So welcome to the course. I just wanted to start off with a bit of an outline of what we are going to be covering so that you can get geared up and fired up, ready to start. So the three sections of this mini course are going to be the introduction, where we'll talk about the fundamentals of clean code, my rules for clean code, digging into those rules a little bit and trying to understand what they actually mean and try and understand them through a few examples, although not too many examples at this stage, as we're going to be looking in more detail once we get to how to actually apply these as programming patterns and how programming patterns lead to implementing some of these rules. So that would be the subject of the second section, where we're going to study the top programming patterns. We're going to understand how they work, how they implement some of these rules of best programming practices, and really try to understand how we would arrive at these patterns ourselves so that we know when to implement them, when to use them, and most importantly, when not to. And then finally, the final section, just a quick wrap up, I'll share with you some of my favorite resources for learning about more programming patterns that aren't covered in this course, as well as some bonus content. In particular, there's a lecture in there about the solid principles. So if you are interested or heard of those, then you will see that that is in the end of this course. So let's talk about some of the patterns that I'm going to go over in this course. So we're going to look at the Mighty Observer pattern, one that you may have heard of before, incredibly useful, get to use it all the time, and sort of language support for it in Unity and C#. The Singleton pattern, again, a mighty pattern that lots of you will have heard about. It's very controversial. We'll talk about the controversy. There's the Finite State Machine and State Pattern. These two are kind of interlinked, as you can kind of use the state pattern to implement a finite state machine. Very useful in games and things like AI. So we will be talking about that and applying it. There's object pooling, again, incredibly useful in games for performance. We'll talk about when you use it and how you can use it. There's, again, some built-in tools in Unity, so I'll be covering those. There's the strategy, decorator, and composite pattern trinity, which are similar but all quite different and play different roles, and you can use them together to great effect. And I have done in the RPG series to create something like a special abilities system. So these kinds of things are very useful in games again. And then finally, we're going to talk about some UI programming patterns, MVC, Model View Controller, Model View Presenter, and Model View View Model, which is a little bit more exotic. And we'll be talking about those and how we can implement them and which one's most appropriate for a Unity Games project. So that's what's coming up. I'm really excited to bring it to you. Dive in and get started. So let me start out by making this rather clickbaity statement and say that you shouldn't use design patterns, at least not in the way that you typically think. We don't use design patterns as a library of tools that we hammer into any problem. This is called the golden hammer syndrome. If you happen to know a tool really well, such as a hammer, then everything you look at, even a screw, is going to look like a nail, and you're going to want to use that hammer to solve the problem. This can happen with design patterns. People will get familiar with one or two. They will love those design patterns, understand them really well, and whenever there is a problem, they might think about applying the design patterns they know. This is the wrong way round. We should be looking at the problems and trying to solve those root cause problems rather than trying to find a solution that fits. It's good to study design patterns as a way of seeing how certain templates of problems have been solved, but often you'll find that once you're really good at programming and design patterns, you find yourself writing design patterns and then only later realizing that you used a design pattern. That's the thing about design patterns. It's often very easy, once you understand the reasoning behind them, to just simply reinvent them as you need them. However, in this course, we are going to study them as a way to reinforce our understanding of good programming principles. So what are those good programming principles? Well, I've put together my 10 coding commandments which as a proviso I should say are more like guidelines, because a good programmer will also know when to break the rules. These are things that I've put together and learnt in my experience as a programmer. You may come up with different ones, you may disagree with some of mine, that's great. It happens all the time with programmers. Programmers like to disagree with each other, so do mention in the comments on this video if you disagree, if you have other coding commandments or best practices that you think should be included here. I went for 10. There are obviously loads more, but 10 is a good number when you're talking about commandments. So commandment number 1 is thy code shall read like English or Spanish or Italian or whatever language you happen to write your code in. Typically people all over the world write in English, which is why I've written the rule like this. And importantly, that should be without even having to include any comments. I think that code should be self-documenting where possible. That means that the variable names and the function names and the class names should really explain what this code is doing, which takes me on to point number 2. Thou shalt take time to name things well. Naming things well is really hard, as we will see a little bit in the next lecture, and so you must take time to think very carefully about good names for things. Giving a good name to something is incredibly powerful. It allows you to reason about it in a way that you couldn't when you didn't have a name for it. Imagine trying to talk about a tree with the word tree. If you were just talking about that big woody leafy thing all the time, you just wouldn't be able to have a decent arboreal conversation. So naming things is important, and we should take time to do it. It allows us to read the code easily. It allows us to comprehend our code. Takes us on to point number 3. Thy classes shall do one thing. By this, we mean that they are at a consistent level of abstraction. If you have got an audio class, an audio player, then it should only do things relating to playing audio. It should not do anything to animation. That is obviously outside of the remit of the one thing that class should do. Now, obviously, the levels of abstraction here can change. You could have a class that's responsible for playing the entirety of your game. Obviously, within that remit, it does a lot of things, but it probably farms out some of that work. Similarly, you have a class that is super narrow-minded that just perhaps spawns an object. And that goes for functions too. Functions should just do one thing. You don't want a function that is print this error message and then do that, print this error message and then do that. You want functions that just do one thing within their level of... Again, they'll usually be a lower level of abstraction than the classes they reside within, but that's the important part. Number 4, thou shalt use as little state as possible. We'll get into why this is a problem in the next lecture. Often a source of bugs is that you've got mutable state, things that can change, variables that can change, and each variable that can change represents a different state that your program could be in. The more variables you have, it gets exponentially more states that your program can be in, and so these are more states for your program to go wrong in. So using less of that makes your program easier to reason about and less bug prone. We'll talk a lot more about all of these points throughout the course, so this is just an overview at this stage. We'll go into far more detail, so don't worry if you don't understand everything at this stage. Thou shalt not refactor before the 3rd repetition. This is point number 5. And essentially what it's saying, that we need to be able to see a pattern before we refactor for that pattern. If you've done something twice, it may not be a pattern yet. It might not be something that needs a method taking out or a class creating or any of that stuff until you've done something that for the 3rd time often, then you might find that it is time to create a new function to abstract that shared functionality or a new inheritance hierarchy. Those kinds of things, usually you need a pattern emerging first, so don't do that too early. Number 6, thou shalt not use static and global state. Again, we'll see this in a couple of lectures' time. It goes hand in hand with point number 4, which is to use as little state as possible. Global and static state is doubly bad because it's more state, but also it can be changed anywhere and accessed anywhere in your program, so it has a lot more possibility to go wrong and to make other things go wrong in your code. Commandment 7, thy classes shall be highly cohesive, goes hand in hand with Commandment 8, thy classes shall be loosely coupled. If you have never heard of these two terms before, I'm going to go into detail on these in a couple of lectures time, so hold your horses and we will understand it better then. Commandment number 9, thou shalt use composition over inheritance. You may have come across the idea of composition. You almost certainly came across the idea of inheritance. Inheritance is where a class is said to be is a something. So, for example, you might have a crocodile is an animal. Those are the kind of is a relationships. Composition is typically a has a relationship. A car has a wheel. So you might have a car has a wheel. So you might have a car class which has a wheel class. And typically we prefer to use composition in programming because it allows us for a lot more flexibility. Again, we'll cover this a lot more in a couple of lectures time. And finally, 10th commandment, thou shalt follow the law of Demeter. I find this the kind of the least important of the commandments, but it is a useful guideline, and as we'll see later, I will indeed be calling it the guideline of Demeter because I think it is a rule that you will be breaking reasonably often, which is why I put it as the last commandment. Okay, so these are my 10 coding commandments. I'd be interested to know what your best practices are. Please go and share them in the comments. And we're going to be using these best programming principles to understand and evaluate the design patterns that we will see later in the course. But in the next couple of lectures, we're going to dive into a few of these to try and unpack why they are important. So here is a very commonly repeated quote about computer science. There are only two hard things in computer science: cache invalidation and naming things. This is usually attributed to Phil Carlton, an engineer who worked at Silicon Graphics and Netscape, among other famous companies. And this is a very, sometimes added to this quote, by the way, is and by one errors. So there's only two hard things: cache invalidation, naming things, and off by one errors. I tend to think that really the first two are the most important, although that second one is kind of funny. So what is cache invalidation? We'll get to naming things in just a second. I think it's the easiest thing to unpack, but cache invalidation doesn't necessarily mean something if you haven't necessarily got a theoretical grounding in computer science. So what do we mean by caching? Well, caching is when we store a value that, for performance reasons or for ease, we could have just calculated. So, for example, we've got a square, and the only information we need to know about or rectangle in this case, only thing we need to know about a rectangle is its width and height. And from that, we can have set width, set height on this, if this was a class. We could also have a get area method, and we could calculate the area using the width and height by multiplying them. However, if we decided, we want to do this for performance reasons, or just for simplicity's sake, we didn't feel like writing a getter, we'd just go and store the area in a new variable. So we've just added another piece of state, another variable into the mix in this class. And because it's a cache, because it is derived from other data and could easily be rederived, there's a problem of invalidating this cache. Every time I call set width or set height, I need to remember to write code that updates the area. Otherwise, this cache becomes invalid. The variable stored in the area is now no longer the real area, not representing the current width and height of this rectangle. So that all seems like, okay, well, I've just got to remember to store it in two variables. I can go ahead and do that. And at the time, that will seem like a good idea. Then somebody else will come along and write a method like double width and height. And they won't remember or won't know that area is a cache and needs to be updated every time width and height is updated. So they just go ahead and naively double the width and height and think everything will be fine. It isn't. Area becomes invalid every time this method is called, and that is how bugs are introduced via cache invalidation. Now, this is a trivial example. However, in reality, these bugs get far more obscure and hard to pick up. So that's why it's really important whenever introducing new variables that you think very carefully about, am I caching something? Could I just calculate this some other how? Here are a couple of common signs that you can look out for just to save yourself the hassle of introducing the caching in the first place. If in doubt, calculate, don't cache, and even if it's not that efficient, you think it might cost you something in terms of efficiency in the long run, trust me, it probably won't, and it will cost you in terms of bugs. So a common thing to see is Boolean flags. If you've got a Boolean around the place, for some reason, Booleans tend not to be state. There are some states, but for example, a common Boolean flag might be is jumping. Could you not calculate whether you are off the ground instead? Is there some other way that you could calculate whether you're jumping rather than storing a Boolean variable about that? It's probably derived state. You can probably, in a lot of cases with Boolean flags, you can calculate that from some other state. So that's an important one. Get components. So this is Unity specific. When you have get components and store the result of that in awake, you're actually caching the result of that. What happens if a new component is added later on? What happens if that component gets deleted and a new one gets created? Your cache, your pointer to that get component will go out of date. Now, this is reasonably safe Unity and probably one that you can ignore, but just be aware that that is a cache that you're creating there. It is not necessarily... If you think of the state as being what is the current component on this game object, you're not necessarily going to get that. You're going to get the component that was on the game object at awake. So that was a cache. Having to remember to update something in code. So if you've got some function and you always find yourself saying to yourself, I need to remember that needs to be updated, then you probably have a cache. Updating variables on callbacks is quite a common one. If like on collision and on collision enter, on collision exit, you find yourself, you're again updating something like a Boolean flag or maybe something else, you might find that you have got yourself into a situation where you're having to do that with callbacks because you are trying to keep a cache up to date. It's not to say that all caches are bad and that you shouldn't ever cache, but avoid it if you can help it. Now on to the slightly easier good naming part of that quote. Here are some good naming tips. So typically the measure of code quality is WTFs per minute, or at least that's a nice way to think about it. You want to have whoever is looking at your code be confused as few times as possible when they're reading it. And that includes you in the future. So you want to name things so that everybody understands what you're talking about. That's where good naming comes in. It's all about good communication. Ultimately, code is communication. Something like this is terrible. You've got an integer named t, and then in a comment you're saying seconds since the event happened. So seconds since, I don't know, something like the character was shot or the character died. Those kinds of things. But you've called the variable t. So anywhere where you're using this in the code, you'd have to go and find this place where it's declared, find the comment. You're going to go, WTF, what is this t about? What am I supposed to do with it? If you'd named it something sensible to begin with, like seconds since event happened, even if it's a long variable name, everywhere that variable is used, you will know exactly what it's for, and it's going to be clear to the reader of the code, including yourself in the future, do. General rule of good practice is that classes should be named as nouns. Avoid names such as manager, controller, processor. It's really not clear what a manager does or what a controller or processor do. They are kind of cop-out names, in my opinion. We add them because we don't really know what this thing is supposed to do. It's an audio manager. What does it do with audio? What exactly is its purpose? Is it an audio source? Is it an audio player? Things like that are much more meaningful than calling it a manager, a controller, or processor. So if you find yourself, and I find this quite often, that I want to call something a manager, stop and ask yourself, what does it actually do? What do I really want to call this thing? Methods should be verbs typically, so you do something with a method to class, which is a noun. So those are good rules to follow in terms of object-oriented programming. And be consistent. Once you've chosen to call something, use that term all the time. Don't go switching between terms and confusing the heck out of somebody who is reading it. Something like fetch value and then later having a get value and a retrieve value will leave people wondering, Is fetch different to get, or is retrieve different to fetch? You just don't know as the reader of that code. If you have chosen the exact same word, then you are sure that the same thing is probably happening. And finally, if you're not sure, go and talk to somebody else about how to name something. You'll often find that they go, oh, well, what you're talking about is blah, 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 and they know exactly what word you intended to use, or so on. I will often find that I have very lengthy discussions about naming something well. We do this inside the team very regularly. We'll go and talk about, like, what should we call this? And we'll spend 15, 20 minutes talking about having something very specific. And that's because naming's so important in communication. So don't underrate it. Spend time on it. Good naming will save you a lot of time later on. So there are going to be lots of challenges like this one in this course to share your own examples from your own experience, because I think this is much more interesting than my clinical examples that I can come up with on the spot. So where have you used cache in your code? Go and share in the discussions for this lecture. Where have you cached something? Where have you ever had a cache invalidation bug? Not everyone will have had this if you've been programming for a short while, but if you've been programming for a long while, I'm sure you can. You point to any cases where you're like, darn it, I should have updated that variable and I forgot to, and it a bug. What is your variable name of shame? What is the worst name you've given to a variable, function, or class? And let me know down in the discussions. I would love to read and share my own there as well. In the next lecture, we're going to be looking at the sources of spaghettifying in your code. And I'm not talking about the kind of tasty sources, I'm talking about the points where they originate from. Let's dive in to that lecture. So let's discuss a few of the sources of spaghetti code. But before we do that, let's ask ourselves, why is it called spaghetti code in the first place? It might not be obvious to all of you. So if you've heard this term before, what it's getting at is the idea that when you've got a bowl of spaghetti like this and you pull at one strand, you're not sure which bits of the bowl are going to move. Where is the end of that spaghetti? Where is it? It's in a tangle. You can't quite see. Spaghetti code is like this. You change one bit of code and you are not sure what the repercussions are going to be. It could be wide-reaching and have a bug in a piece of completely unrelated code, or at least you thought it was unrelated. So that's why spaghetti code is bad, because you go and make a change in one place and it has repercussions all over the place. What we want is you make a change in one class and it's mostly self-contained to that class with a little bit of changes elsewhere. Now, the static and global state are some commonly, identified issues with code. Any use of static and global state is a bad thing. So what do we mean by static or global state? Well, it's these cases where you have a static public variable, even not necessarily public, but a static variable that's shared across the whole of your program, and you can edit it. If it's constant, that doesn't produce a bug that way. But if it's something that can be modified by your program, then there is an issue. Here's why. Bugs, that's the first thing. It's quite easy for that variable to change when you're not expecting it to, because somewhere else in the code it gets updated, you forgot that, because your mind can't be everywhere in a large code base, and so bugs happen. Poor unit testability. So this is not always a problem in games, because we don't always unit test games for whatever reason. That might be a bad thing, but we don't often unit test games. But if you've got global state, it makes it virtually impossible or very hard to unit test things properly, because you can't set things up in isolation in a little test case. Code comprehension. Because global state variables are often declared far away or used far away from where you're currently reading the code, and their impact can be far away, it can be really hard to understand. When is that variable going to change? What should that variable be at this point in time? So someone coming into your code fresh, or you coming in a few months' time, you won't be able to know what to expect from that variable. Multi-threading, not so much an issue again with Unity because we tend to write single-threaded code, but if you do have multi-threaded stuff, then this whole level of bugs just gets so much worse because threads can stomp all over each other. There can be performance issues around having multiple threads trying to access the same information and communication between threads. Its global state is absolutely a no-go when you've got multi-threading involved. And the last final argument is, and then you need two. So you thought with that global state there'd only ever be one audio manager. You thought there'd only ever be one character in the game. Oh, suddenly we've decided we're going to have a team of player characters in the game. And now you thought that it was all right to have just one global mana variable. Well, now we need two mana variables, one for the player one and one for player two. Wouldn't it have been better if we hadn't used global variables in the first place? So these are some of the common reasons we don't use global state. It creates spaghetti code where we don't know what is involved with what. Here's an example. Suppose we had a mana variable, like I was saying, and we decided it'd be a good idea if this was a publicly static global variable. So in our character, we might decide that we're updating the mana every frame to recharge, and when you use an ability, that cost gets subtracted from the mana. Obviously, we'd put in some code here to make sure the mana doesn't go below 0 and stuff like that, but for simplicity's sake, we're just leaving it like this. Now, suppose you have another class somewhere else, a magic potion, that will restore your mana. Now, for simplicity, because it can just get access to the mana, it just does. It goes and restores that mana. Everything's working fine at the moment. What if I went in and added some code that tried to cap the mana? Well, I would go and write it here where the mana is being updated, right? Yes, except I'd introduce a bug because I could overcharge the mana by using a mana potion because I'm accessing this global state and realize it was coming out of left field for me. I didn't know it was there. Another source of spaghettification is communication between classes. And this is where those 2 points of high cohesion and loose coupling come into the equation. So what is loose coupling and high cohesion? Well, I think this diagram kind of sums it up the best. Imagine that these boxes are classes, and inside them the dots are variables and functions. And the lines between them are when a function accesses a variable or another function, and so on. So what's going on here is the good example at the top is one which has high cohesion and loose coupling. What do we mean by that? High cohesion means that the elements within the classes, the functions and variables, refer a lot to one another. The functions use multiple variables, they use each other, and so on. Loose coupling means the opposite is true between classes. One cannot try to access lots and lots of variables of another class. That's what happens when you have the bad example down here at the bottom, which is one that has low cohesion, meaning that the elements within the class don't really refer to each other very much, and tight coupling, which is when they actually refer a lot more to elements from other classes. You can see these two classes have a lot of functions and variables that reference each other across the class boundary, which means that these two classes are very tightly coupled. And this is your structure of classes isn't very good, and you should consider rejigging the classes and their responsibilities so that they can be have higher cohesion and more loose coupling. So here comes an example of this and a challenge for you. Why are these two classes here bad? Pause the video and have a go and see if you could also rewrite it to be better. Okay, so this, if you hadn't figured it out, it was low cohesion and tight coupling was what was wrong with these classes. So here's our low cohesion character class, which you can see what's low cohesion about it. Well, this knockback method only uses one variable, the animator. The shout method only uses the audio source and the shout, and take damage only uses the health. So you can see that essentially we've almost got three separate classes here. We've got one that deals with the animation portion, which is this knockback method, one class that deals with the audio portion, and one class that deals with the health portion. So it's not very cohesive. We could split it up and there wouldn't be much communication between those classes, and we'd end up with more high cohesion. Now, how about the tightly coupled enemy was the other problem, because this enemy knew an awful lot of information about the character. For instance, it knew all of these methods. It used 3 of its methods here when it only has 3, so that's pretty tightly coupled. And then we all how to access and how to find this character. So in start, it's actually finding the character. That's another thing that it needs to know about that class. And if we change where the character is located, if we changed any of these methods, they're all reasons why we would have to come and also change the enemy. So spaghetti code is when you make one change in one file and you have to change 15 other files. Good code, you should make a change in one file, maybe 2, but that should be it. If it's good code, it's resilient to changing and doesn't need scattershot surgery across the whole code base. So how could we improve this? In a high cohesion character, we might say, well, let's take more responsibility for taking a hit, and that's going to be all rolled up into one method which accesses Demeter, the audio, and the health components of this character. This is now a high cohesion class because the function accesses multiple of those variables and it's much more tightly integrated. The loosely coupled enemy, on the other hand, might just, and this is why they go hand in hand, high cohesion and loose coupling, because now that we have a high cohesion character, the coupling to the enemy has improved because we now just call take hit. What I've also improved here is we've used an interface. If you've not seen interfaces before, they're just a way of saying, I want this, it's basically, I want this method to be implemented on whatever object is passed in. So now what we've got is that instead of relying directly on the high cohesion character class, we could even swap that out. Instead of having a character, we could have an NPC object. As long as it implemented I attackable, we would be able to call take hit on it. So now we don't even have we're not even coupled to the way of finding that class in enemy. We just get past that target, and that's how we do the damage to it. Now, obviously, this is quite a toy example, but you can see from this example how cohesion and coupling go hand in hand. Now, in the next lecture, we are going to look at composition and inheritance and why you should prefer the former over the latter. I'll see you there. So the next point I want to dig into is point 9, thou shalt use composition over inheritance. What does composition and inheritance mean? Why should we prefer one over the other? Composition over inheritance. So a classic example of where inheritance can go wrong is the following. Imagine we start off with an animal class, and that's going to be our superclass. It's going to be what we inherit from. If you're not too familiar with inheritance, this is where we take all of the functionality of this class. Essentially, we say anything that inherits from it is one of these. It has all of that and more. So a mammal, for example, might be a type of animal. Not all animals are mammals, but all mammals are animals. And so a mammal will have all of the functionality of the animal. It will be an animal. So if an animal has a live method implemented here, then an animal also has that live method. It automatically inherits that from the animal class. The mammal, however, can add its own functionality as well. As you can see here, the mammal adds on the functionality of being able to make milk, and anything that inherits from the mammal will be able to make milk. We might have another subclass of animal which further specializes it or specializes it differently to the mammal, such as reptile, which allows it to lay eggs. That gives it that functionality there. And then we can actually inherit some actual instances or some actual classes from this that we might instantiate, such as the cow or a snake from reptile. And you can see how they're going to get all of the appropriate functionality here. Cow gets to make milk and live. The snake lay eggs and live. And they share the common functionality of living, but they get to differentiate functionality as well. This all seems fine and glorious and really easy up until the point where you find something that doesn't match your inheritance taxonomy. enemy. So you might find something like a platypus, which suddenly doesn't inherit from mammal very easily because it wants to be able to lay eggs, but it doesn't inherit from reptiles. It's warm-blooded and it needs to make milk. So where do we inherit from? And this is a very common issue with inheritance. You'll find that stuff kind of starts to happen. You'll find things that you want to inherit from multiple places, and languages like C# will not let you inherit from multiple places, because then you wouldn't know, for example, if I were to call the live method on platypus, do I call it via the mammal side or the reptile side? What if the reptile had overridden it? And so it gets very confusing. And obviously a platypus isn't really a reptile, but it does have the ability to lay eggs, so this gets very confusing. Composition, on the other hand, it can be a lot more powerful. It can be a lot more verbose as well. It can mean that we have to write methods that expose the functionality of these components. It can be a little bit more complicated than inheritance, but it can save us a lot of that kind of hassle. So you may be familiar with composition in the Unity components. We can take a game object and add all sorts of different components to make it behave how we want it to. So instead of having a player class, we would have a player game object, and we would give it a movement component, we would give it some particle effect components, we'd give it some animator components, and that, the combination of those components, the composition of those components, gives it its actual functionality, and those components have to coordinate between themselves. So we could do the same thing with a cow, and in this case you could still have a coordinating class. You could still have a cow class that coordinates and composes a bunch of functionality driven components. So for example, we might have a milk making component. The cow will have a, so you notice the change in language here. In inheritance we talk about is a, we would say the cow is a mammal. Here we're saying that the cow has a milk making component, and it would need to write some wrapper functionality to make sure it is calling to that make milk function in the right places and so on and so forth, but it is able to reuse that functionality at will. And the snake could have an egg laying component and similarly could call to that functionality. And now the platypus has got a very easy choice of simply including both, being able to have a milk making component and have an egg laying component. And composition and inheritance isn't an either or situation. You could easily have both of these. You could have that the mammal has a milk making component, that you have the reptile has an egg laying component, and then the platypus is a mammal but also has an egg laying component. So you can start to mix and match these things as well. But what we're saying here is that try and put more of your heavy functionality into components. They are far more reusable, they are far more flexible than trying to stuff all of that functionality into parent classes and an inheritance. Try and use the inheritance as little as possible, try and use components as much as possible. And that's what composition over inheritance means. It is not a hard and fast rule saying that you must use composition all the time and never use inheritance. It's saying try to use one more than the other. Let's have a little challenge to see if you can figure out where this picture goes wrong. This is an inheritance hierarchy, and what I've listed out is some of the functionality that you might expect to see in these classes. So at the top level, we've got a character. This is the shared functionality between a player and an enemy. It is able to locomotion, so moving around the world. It's able to attack. It has health. These kinds of things we want both the player and enemy to have. Great. So we inherit in player and enemy from the character class. The player adds a layer of player control logic. It also adds some upgradability, such as maybe in an RPG, you're able to level up your character. The enemy, on the other hand, does not have this upgradability. Enemies are kind of more fixed and programmed into the level. However, they do have AI control, and they are programmed to be hostile to the player when you approach them. This seems fine and great, but can you imagine what you might add to this game that would break or encourage you to have bad inheritance here or mean duplicated code? Have a pause, have a think, see if you can think of anything, any type of class here that we'd add and wouldn't match in here. Okay, so what I'm thinking is we could be adding in an NPC, for example. An NPC would need some shared functionality from the character. It would need the locomotion. It would need to be able to, probably wouldn't need to be able to attack. So it's going to inherit functionality it doesn't need. So that's something that's not great already. It's going to inherit a health. Maybe you don't want to be able to kill the NPCs. So maybe it shouldn't be inheriting health either. So you can see how inheritance is already getting us in a muddle without the fact that actually now we're going to have some duplicated code, because we might might want to have AI control and share some of that AI control that the enemy's already got, but without the hostility to the player. So we don't want to inherit NPC from enemy, because then it's going to be hostile to the player, and somehow we've got to switch that off, and that's going to be a bit hacky. It doesn't really make sense that an NPC is an enemy. That doesn't make sense from an inherent point. And one more thing that we can see here is that these classes are violating the principle that a class should do one thing. You can see they are managing many different domains. They are managing locomotion, they are managing combat, health, AI control, all that sort of thing. If we split this into components, it would help on multiple levels. It would allow us to compose something like an NPC very easily. We could include locomotion components, but we could exclude health and attacking. We could include AI control components, but exclude the hostile to the player components. And that makes a lot more sense. Now, what you can do to get a bit of the best of both worlds, and particularly in Unity, is to use the prefabbing system as a kind of layer of inheritance, which would allow you to, say, have a character prefab and then inherit from that, and maybe your NPC wouldn't even inherit from character because all you're doing is adding that locomotion component, but it allows you to group together some of those common groupings of components and have still a kind of inheritance structure for when that is useful. So hopefully you now understand a little bit better why composition is a good idea, why inheritance sometimes leads us into trouble. In the next lecture, we're going to be looking into the rather obscurely named Law of Demeter. So what is this Law of Demeter, or as I'm choosing to call it, the guideline of Demeter, because I don't think it's something that we want to adhere to necessarily too strictly. It needs a little bit of caution when applying it. Now, typically it's referred to as the dots rule, or the multiple rule, or the two dots rule. And the idea is that if you see a line like this, you're almost certainly in violation of the law. And let's have a look at this. Why is this a bad thing? Because we've got a class we're in, so it has an enemy variable. Maybe that was something passed in as an argument to a function. So we have a dependency on enemy in this class. That's fine. We know about the interface of enemy, so doing a get current target on enemy should be fine. That's a publicly exposed variable. We are depending upon the interface. That is okay. However, what's not okay is that then this target is of some other type. Maybe it's a player, for example. Maybe it's a character. And we are now calling a function on that. So now we're depending upon that class as well. And then what's more, we've done another bad thing. This would have been bad enough. We're going one step further and we're saying, well, apart from depending upon the enemy's target class and the health component, now we're depending on the health component to do damage to it. Basically, this line is bad because it means that we're depending on every link of this chain. If anything in this chain changes, then we've got ourselves a problem. Now, this wouldn't be so much of a problem if everything in this chain was the same. Sometimes in some languages like Ruby, you'll do this a lot with strings. You'll have chains of string commands or chain of array commands, and each member of the chain just returns another array or another string. So you're not actually increasing the number of classes you're depending upon. But this isn't the case here. Here we are depending on more and more classes, and that's basically the reason that we have the Law of Demeter, because we don't want to, or the Law of Demeter, as some people pronounce it differently. That's how I pronounce it, and it might be wrong. Anyway, the reason we don't want to do this is we don't want to add more class dependencies, and this is an easy way of accidentally adding more class dependencies and not realizing it. It's not the best. Often what we want to do is make the class we're talking to have the responsibility for doing more of this. So exposing something higher level from the enemy might be a solution, such as doing damage to the current target. So that means that the enemy will have to have more code written into it. Maybe the current target and the health component also will need to have more code written into them to avoid these multiple steps. But that does now mean that if we made some sort of wholesale change to the way that the target works, you're not going to have to go and a whole bunch of other files that are doing lookups, crazy lookups like this. So here's a challenge for you to see if you can identify what is wrong with the code on this slide. So what's the situation here? We've got ourselves a player set up, a player's got a gun, the gun has got ammo, and the ammo class has got a number of rounds. And for some sake, I've made these variables public, although you could imagine that they were private with getters and so on and so forth, but for simplicity's sake, everything's public in this hierarchy. Then over on the left, we've got some UI to represent the player and represent the gun and the ammo. And this works fairly straightforwardly. We've got a player UI which has some gun UI in it. And when we redraw the player UI, we get some information about the player. You can see we're getting reference to we are printing its health. In lieu of actually updating some UI, we are printing the health. We are calling redraw on the gun UI. And the gun UI similarly gets some information from the player and prints the rounds left. What looks wrong in this slide? Pause the video and see if you can figure it out. And if you can figure out what's wrong, a bonus is to try and fix it. Okay, welcome back. So if you've had a go at this, then you will be saying, well, this line here looks a bit fishy. That seems to violate the law of Demeter because our gun UI has to have a dependency on player, has to have a dependency on gun, has to have a dependency on ammo, and it has to have a dependency on rounds left. Doesn't seem ideal. So what could we do to improve this situation? Well, it's not always as straightforward as saying, well, let's just have the player have a get rounds left method. Maybe that's the wrong level of abstraction for the player. I think here the first place we're going wrong is by having the gun UI get hold of the player for itself. The gun UI doesn't really have to be linked to a pool. It could just be passed a gun or given a gun from somewhere else. So let's see if we can't do a better job of this. So the first thing I said was over in the gun UI, I think we want to not worry about getting hold of the player here in the UI. In fact, I don't even think we should know about the player at all. It's a gun UI, it's not a player gun UI. So let's try and reduce the number of dependencies here by passing in the actual gun type here that we want to redraw, that we want to render. So now what we can do is we've simplified matters a little bit. We've got none of this dealing with the player or figuring out how to get hold of the player. And instead we are just getting hold of the gun.ammo.rounds left. This is still not great, but we'll come back to that in a second. The player UI now would be the one responsible. When it calls gun UI and does a gun UI.redraw UI, it would pass in the player.gun. And that's fine because it has a dependency on player. It has an unfortunate dependency that I don't quite like, but we can probably not get around at this level, which is that it knows how to find player as well. That's not ideal, but it's probably okay. And it can use, obviously, the public interface for player. It can get its health, it can get its gun, and redraw the gun using the gun UI, which it's aware of. So this is no longer so bad. It's not violating the law as badly, but there is still a gun.ammo.rounds left. So we've got an issue here that the gun UI knows a little bit about the internals of the gun and how it's storing the rounds left of ammo. And if we were to change how that works, it's going to affect the gun UI. So this is where we do the kind of simpler change of just adding another getter in here in the gun, where we might do something like public, which returns an int, which would be something like get rounds left on here. And we could just go ahead and from here return the ammo dot rounds left. And now you can see the gun had already a dependency on ammo, so it's fine for it to be getting the rounds left from ammo. It's using its public interface of its direct dependencies, not dependencies of dependencies. And that's the point of the law of Demeter. So now we can fix that up over in the gun UI. So instead of the gun UI knowing about the ammo class, it just does a gun.get rounds left, and that means that the gun UI only has a dependency on gun. The player UI only has a dependency on player and not any of its descendant dependencies. And the gun only has a dependency on its ammo, and so on. So we've really reduced those dependencies down to the direct dependencies that are absolutely necessary by using the law of Demeter. So hopefully now you'll be more confident in understanding if you ever come across the law of Demeter or Demeter and don't know what it meant in the past. Now you've got an idea and can see how it can help you to write better, more maintainable code with fewer dependencies. So this brings us to the close of our introductory section. Let's review our coding commandments before we dive in to design pattern. Number 1, thy code shall read like English. Number 2, thou shalt take time to name things well. We've seen how important and hard that is. Thy classes shall do one thing, also known as the single responsibility principle, and this is about consistent levels of abstraction. Thou shalt use as little state as possible. State causes bugs. Let's not include as much of it as we can. Thou shalt not refactor before the third repetition. Premature refactoring leads to complication, not simplification. Thou shalt not use static and global state. State is bad, static and global state doubly so. Thy classes shall be highly cohesive, and thy classes shall be loosely coupled, meaning that they communicate a lot within themselves and less outside of themselves. Thou shalt use composition over inheritance because it's more flexible and generally more reusable. And thou shalt follow the law of Demeter to not include dependencies that we don't need. I look forward to seeing you in the next section where we'll get cracking with design patterns. So let's talk about one of the most commonly used design patterns, or the most commonly talked about, which is the observer pattern. And we're going to start with a motivating example from the game world. So imagine that in my game, I have a rampage mode. I get some sort of power up, and I become invincible and scary to enemies. So usually enemies will try to attack me. However, if I get a rampage power-up, I become invincible. And as a result, enemies should try to run away now. But a few other things happen in the game as well. Apart from that, that's not the only behavior that people see. They will also see that their health component should stop registering damage, and that the UI should be tinted red or some other kind of UI update and indicator. So the situation we've got is a lot of dependencies. We've got a rampage mode component of some sort, which gets enabled when we pick up that power up. It kind of detects the power up somehow. Let's just assume that that bit is sorted out. We've got the rampage mode has to talk to a whole bunch of enemies. It has to call a method on the enemies to say, hey, you should be scared of me right now. So in a naive example, this might do a find object of type, find all the enemy AIs and call a method on them saying run away, something like that. Now, this has obviously created a dependency between Rampage and the enemy AI. It's made Rampage dependent and coupled to the enemy AI. It also, if we carry on with this naive of a Rampage UI, it has to go and say, hey, get the UI and update it. Tell the UI that we're in Rampage mode and draw the red tint. And go to the health component and say, hey, enable invulnerability. So it's got all of these dependencies all of a sudden. It knows a lot about all of these different classes, which is not an ideal situation to be in. What we want to do is essentially flip this around, because this would take it from having one class with a dependency on lots of classes to a lot of classes having a dependency on one class, which is a much better place to be in this case. And one naive way of doing this is in update. So the Rampage UI could, every update, check the player's Rampage component and say, are you rampaging? And if so, I should draw the Rampage UI. The same could go with the health component. It could check against Rampage and it could enable its invulnerability, and all of the enemies could run their update methods to check that as well. Now, this has an efficiency because update will be run every frame, and Rampage might be an event that happens once or twice in the whole course of the game. So this is an okay strategy, but not ideal. And it's also not great from the point of view of understanding the code. So what could we do instead? So that's where the observer pattern comes in. Now I'm going to use this graphic, which is a UML diagram taken from Wikipedia, because I think it's time that we start to understand these kinds of diagrams. We use them all over the place wherever design or programming patterns are discussed. So we're going to try and understand what this means. So the key things in the observer pattern are the observer class, which is this thing over here, and the subject, which is something over here. The subject is the thing that we are observing. the observer is the thing doing the observing. In our example, the subject here would be the rampage component. The observers would be a number of different classes. They would be the enemy class, the rampage UI class, and the health class. So what's going on here? Basically, the observer has an update method, which basically is saying something has changed. For example, rampage has started, rampage has stopped. That would be our update method on the observer. And then you can see what we've got here, this arrow, this empty white arrow is indicating inheritance. So we've got a concrete observer A, a concrete observer B. In our example, this would be an enemy, this would be a health component, and the ramp UI. Each of these implements the update method, so each of them would have rampage enabled, rampage disabled on them, and you can then have a situation where they register themselves or notifications. So you can see the subject here has a register observer, unregister observer, and notify observers. So what would happen is the health component would call register observer on the enemies would do the same, and then when the rampage actually starts, the subject, in which case the rampage component, would notify all of the observers. It essentially runs through, as you can see this little snippet of code here, notify observers would go and do a for loop over all of the registered observers and call their update method. So this is obviously not exclusive to rampaging, and it is a very common pattern to want to use when in a situation where you have a one-to-many kind of communication, where you have one class, the subject, that wants to send a message to lots of different observers and doesn't particularly care who those observers are. We don't want to have to know who needs to update as a response to this. It's just a fire and forget kind of situation. Now, there's a lot of ways for us to do this. The kind of classic way is to implement all these methods, but there's a lot of better ways for us to do this in Unity and C#. So we're going to look at some of those methods in the next lecture. But for now, let's have a quick little challenge about this pattern and have a think about the principles that this pattern is trying to improve. So take a look back at the commandments from the last section, and which does this particular pattern implement? Pause the video and have a little ponder. Okay, welcome back. So what I think this implements is not super clear necessarily straight off the bat, but this is about loose coupling primarily. We had a situation in the first naive implementation of Rampage where Rampage was unnecessarily coupled to a whole lot of components, which is undesirable because any of those components changing would cause a change in Rampage. So what you're doing is you're reducing the coupling essentially by changing the direction of those dependencies, and that's why we like to use things like the observer pattern. Okay, so that's the observer pattern in a nutshell. In the next lecture, we're going to look at how we can actually implement it using various Unity methods. Hello and welcome. In this lecture, we're going to be implementing the observer pattern using Unity events. And if you haven't come across them before, we're going to do a brief overview of them and see how they fit the observer pattern. So let's start with an example to really understand how the observer pattern works in practice and what mechanisms we might use to implement it in Unity and C#. So here we're imagining that I have a game where you can level up. So you can get experience points. This is a level mono behavior here, a level component. And we've got experience is basically the only state of this class, the configuration, how quickly it gains experience over time. This is just a very simple little hack so that we don't actually have to implement any gameplay, where in this method here, if you're not familiar with coroutines, this is a coroutine. And what it's doing is you can basically see it like this. It repeats, it loops around, it waits 2 seconds, and then it gains 10 experience. So it just keeps gaining 10 experience every 0.2 seconds. That's how it levels up. And the configuration here is the points per level. So this goes back to my point about not caching stuff. We don't have, you notice, a variable tells you what level you are because you can calculate that from your experience points. So if we go down to the get level method, you can see that it's simply the experience points divided by the points per level. And because these are both integers, this ends up being an integer division. And if you have less than the points per level, you are level 0. Once you have, say, 200 points, you then are level 1. Until you have points, then you're level 2, etc. Get experience, it's pretty straightforward. Gain experience, again, pretty straightforward. Getters and setters here, really. So this is a very basic class. Now, we've got a health component, and this health component kind of has some little hacky logic here. Again, we've got kind of health drain coroutine, and all this is doing, if we go and have a look at it, is it will drain the health down to 0 at whatever drains per second every second. So it just removes something from the health every second. So again, we've got this gameplay little test for us. And at the beginning, we reset the health, so the current health gets reset to the full health in Awake. So then we've got some getters, and we've got a reset health public method, which we might not want to be public. Then finally, there's a debugger mono behavior, which simply every second is putting out the vital stats. It's logging the experience, get level, and get health. Run this. It really does not do very much. You can see in the sample scene here, we've got the observer example, and we've got particle system. If you go ahead and just play, the particle system doesn't run by default. It's been set up to not run on Awake, and we've just got our log messages down here saying the experience as it goes up and up and up. You can see the level that's being calculated and printed here, that's working as I explained, and the health, which is just steadily decreasing and decreasing and decreasing. Now, suppose that in my game I wanted to implement a behavior where my health gets reset whenever I level up. Now, the naive way to do this, if you didn't know about the observer pattern, would be to go into level and say, okay, well, whenever I gain experience, I need to check whether I have leveled up. So before I gain the experience, I'm going to keep a note of what my level was. So I'll say that the level is equal to get level when I start off. So that's kind of made a copy of that initial level. And then after I've gained experience, I can simply say if the new level, so get level, is greater than level, then I can do whatever it was I wanted to do, which in this case would be to get components of type health and to call reset health on that. Obviously, this has created a link that doesn't really make sense. I mean, why should the level component know anything about health? This is a rule more about the health component. It's more that the health component wants to be reset when levels up. So instead of doing this, what you could do is remove all this logic from here. I'm just going to comment it out for a second because it is in a little while. And what you can do instead is you could go ahead and go over to health, and you could decide that we're going to reset health by polling. Polling basically being checking every frame. So we would go into here after Awake, I'd add an update method. In this update method, first of all, I need to be keeping track of the current level to see whether I've leveled up. So for a start, I'm going to have to create a kind of extra piece of state in health to do with level, which is weird, but we'll get to that in a second. Then I'm going to have the last, I'm going to call it last level, that piece of state, which I'm going to set to 0, but I'm actually going to initialize it in start. If we access other things, we shouldn't do it in Awake, we should do it in start. So we're going to do a get component of type level dot get level. We're going to initialize last level to that value. And then in update, what we're going to do is if last level is less than current level, and I need to get the current level into a variable. So let's do an int current level is equal to this same line here, get component level, get level. Notice I'm not caching this level component here, I'm just getting it when I want it. And then if we have increased, then we need to store a new last level first of all. So last level is equal to current level so that we don't go resetting every single frame. And then you can call reset health. This is complicated and it is polling, which means that this is happening every single frame. We're having to check and get the other level and compare, even though we arguably could know. When we did it the other way, when we called it from level, that was much more efficient. It was just the dependencies were all wrong. So what we want to do is for us to be able to subscribe. This is a perfect example of the observer pattern. We've got something that we want to observe, the subject, which is level, and the observer is health, who wants to observe that level. So how can we do that? Well, one way that you can do this in Unity exclusively is using something called a Unity event. Now, I'm going to start with this because although it might not be the most obvious suggestion, it is quite easy to understand. So what you can do is you can create a serialized field that has the type Unity event. And we can call it something like on level up. And you don't have to give it any value at all. It automatically gets set up correctly by Unity. So on level up. Now, what we're going to do with on level up? Well, let's uncomment this code that we had in gain experience. And when we do level up, we can detect that on line 24 with that if statement. We can do on level up dot invoke. So you see that on level, the Unity event has this invoke functionality. Now, what that does is it essentially calls a notification on anybody who's listening to this Unity event. Now, how do we go and listen to the Unity event? Well, there's ways of doing it, but the obvious way is to do this in the inspector. That's why I made it a serialized field. So I can go ahead and remove this start code and update code. We don't need that anymore. Let's get rid of that. We can get rid of the extra state that we included there as well. We don't need that. And then we head into Unity, let it recompile itself. And if you go to the observer example game object, then essentially what we can do is this level script now has this on level up section, and you can add items to this list of observers. And basically what that's going to do is everything in this list will get called when we level up. So for example, we've got a particle system. You can link all sorts of gameplay events to this on level up event. So I can drag in my particle system game object into the object, the target object to run. And then with the function, I need to go ahead and select that I want to run a function on the particle system component. And then I need to go down to whichever function I want to run. In this case, it's going to be the play. And what we can do is observe that if we go ahead and hit play, and we're gaining experience periodically, you should see the log messages down here. When we reach 200, you can see it played a particle effect to signal that I leveled up. I level up again, plays a particle effect again. Every so often it's playing a particle effect in response to that Unity event. This is the observer pattern in action, except it's an observer pattern that isn't fully realized in code. It is configured using the Unity event. It's configured using the Unity editor. So here's a challenge for you to replenish the health using this Unity event that we have just created. Go ahead and add the Unity event and that code that I was writing in the first part of the lecture to the code that you can download as a resource against this lecture. Then add a Unity event callback, a new one. We've got one talking to the particle system. Add a new one, hook it up to the observer example game object, and call the reset health method. So pause the video and have a go. Okay, welcome back. So how are we going to do this? Well, we're going to start off by going into Unity, because we set up these Unity events there. We're going to add a new callback. We're going to drag the observer example as the game object target in here. Then we're going to go to select a function. You can see it's showing us the components that are available that game object. We need to find the health component. We need to go to the reset health. And there you go. We're now calling reset health when we level up. So if we go ahead and hit play, then you can see we're gaining experience, then we level up and our health goes back up to maximum. So we're constantly draining the health, but it also gets reset every time we level up. Great stuff. So that shows how the observer pattern can be implemented using Unity events. In the next lecture, we're going to look at how we can implement it using delegates and actions using C#. Hello and welcome. In this lecture, we are going to be looking at how we could replace the Unity-specific Unity event with a more C# generic event action. And we'll see the pros and cons of using that approach. Let's dive in and see it now. So we've seen how we can implement the observer pattern using a Unity event. However, that does require us to go in and set this up in the editor. And that means that if we use a health component and forget to set it up, this behavior is not going to exist. That might be fine for you, and you might not want it to always exist. But if you want a certain behavior to always exist and be configured in code, then you can still use a Unity event. There is a way to subscribe to a Unity event in code. That's one thing that we could do. But there is a built-in mechanism in C# that we could use as well. So let's first of all have a look at how we might do this in code. So taking this serialized field and turning it into public will expose our onLevelUp. I have accidentally just gone ahead and closed that file, so let's go and open it again. So we've now got onLevelUp exposed. So in health, we should be able to register here. So we're going to do this in start because we need to get hold of another component, and we should only get hold of and communicate with other components in start. We'll do a get component level, and then we are going to look for the onLevelUp public variable Unity event. And from there, we can go and see what options we've got. And we've got an add listener. You can think of a listener as being a bit like an observer. Where you see listener, you can substitute observer if you like. So we can add a listener, and then what you need to pass in here is a function for it to call. So we could pass in reset health, and it's important here that you leave off the set of parentheses, because what we're doing here is we're saying call this method when onLevelUp is invoked. If we put parentheses after here, we would be calling the method right now in start, but that's not what we want to happen. We want that method to be called onLevelUp. So we need to leave off the parentheses. So that's the way that we can do it with a Unity event, and that's okay, but there are a few things that are not so great about this. The first is that this onUp variable has a lot of other methods that are completely unprotected. For example, I can do onLevelUp dot invoke. So I could call the onLevelUp event. Now, obviously, I wouldn't try and do this, but you can see that it's not very well protected. It's not very well encapsulated. I could also remove all listeners. That's not very good for the health component to be able to do. So all these things are fixed by a C# mechanism called an event. And an event automatically protects you. It allows you to publicly expose subscribing to an event and desubscribing yourself, but you can't remove anybody else's listeners. You cannot invoke the method. That can only be done from the place that declares it. So that sounds like exactly the sort of thing we want to be able to do. So let's go ahead and put our Unity event back to being a serialized field, like so. And let's create another onLevelUp event here, which we're going to have as our onLevelUp action. And you'll see why in just a second. The way we declare this is, and I'm going to put this after all of our state, we have a public variable that we put the event keyword in front of. And we're just going to use the type action for now. And we'll get to that in a second. Now, you do need to be using system in order to use action, or you can use system.action. So we've got public event action, and then we can have onLevelUp action, I'm going to call it, just to differentiate from the other one. Now, what we can do with onLevelUp action is we can actually just call it like a method. So if we go down into gain experience where we are invoking onLevelUp, we can also do onLevelUp action, and we can just put parentheses on the end of it and call it like this. So we don't have to do a dot invoke. You can just call it like this because it's built into the C# language. It has some niceties around it. So you can do like this. It does, however, this will give an error. If there is nothing listening to this event, then it's going to give an error when we call this. You will wrap this in an if statement. So you'll say if onLevelUp action, and you notice that's quite cool. There is a little lightning bolt in autocomplete in Visual Studio Code, which basically signifies that it's an action. You may have seen these in other built-in Unity things. So we can put this inside an if statement, and then you can call onLevelUp. Call the method from here, and I was wrong that you can't put it directly in an if statement. You need to say is not equal to null. So we're saying that if onLevelUp action is not equal to null, you can go ahead and call it like so. Now the flip side to this would be registering for that event, so actually being able to go ahead and listen to it. We can do this over in health, Now we've not got on level up exposed anymore, so we need to do on level up action. You can see it now says on level up action. It gives us that little thunderbolt, which tells us right off the bat that this is an action, we can subscribe to it. And then what you do is you use this interesting syntax. You do plus equals, and then you have the name of the method you want it to call, such as reset health. So this does exactly the same thing as when we did add listener, except the syntax is slightly different and, in my opinion, quite nice. So what this is doing is it's saying on start, go ahead and add this reset health listener, and this will be called whenever the level up event happens. So you don't need to do this anymore over in Unity. You don't need to configure this. So we can go ahead and remove the reset health call from the inspector. And that's great. We are now the same sort of functionality. However, let's just check. Is there any way that we could abuse this? Let's go in, do onLevelUp.action dot. Well, actually, we can't do any dots here. There's no kind of dot to be done. What we can do is we can remove a listener. We could remove the listener for reset health. And that's something that we might well actually want to do, because the standard way of doing this in Unity is not to do this in start. Reason being, you might start with a component disabled, and you probably don't want that component to have functions called on it if it's disabled. So what we typically do is, instead of using start, we use on enable, which does get called in start if your component enabled at the beginning of play. So then on enable means that we enable the health component, or we get started, and we then subscribe to having our callback called. So I'd like you to experiment with removing that callback on disable. So add an on disable event. If you don't know how to do that, it's exactly the same as the on enable event I just did, but with the words on disable instead. And then use the minus equal operator to remove that reset health listener, and check the behavior in game. If you go in, play the game, and disable the health component while you're playing, what happens? Does that callback get called anymore? Does the health stop being reset? Have a go, find out. Pause the video and have a go. Okay, let's go back in and give this a stab. I'm going to do an on disable. We're going to do basically the exact same code. So it's going to be a get component level dot on level up action minus equal the reset health this time. Now, actually, because we're not calling reset health from outside anymore, and it's probably not the sort of thing we want just anybody to be able to call, I'm going to go ahead and make that private, and you can do that now. So the level doesn't need it to be public because nobody is using that public interface. The only public interface here is the fact that level exposes an on level up action. And this is the right way, in my opinion, for the dependencies to be going from health to level, not the other way around, even though the direction of execution is the other way around. The level is calling to us, but it doesn't have to know anything about us. That's a great thing about the observer pattern, is it, because it flips those dependencies around when you want them to. So this should now work. Let's go over into Unity, and we're going to make sure that the game isn't going to maximize on load, and go into our console, clear it out, and we're going to go ahead and hit play. So when we go ahead and hit play, it's going to maximize it for some reason. I don't know why. And you can see we're getting our log messages out here. And what I want to do is just go ahead and disable the health component for a time. And we're going to see that the health component carries on running because the coroutine is running. Don't worry, that's a bug with my implementation there, but you can quite clearly see that the health is not being replenished. So we have successfully removed ourselves as a subscriber to the level up event. However, if I go ahead and re-enable it and we level up, you can see the event is being called once again. And that's entirely being configured now in code using events and actions. Now, I did promise that we would go back to reviewing this action type here. So if I go to level and have a look, we've got this action type. Now, basically, this is an easy way of describing a delegate type. And So this is going to get a little bit technical now. If you're not interested, action is all you need. However, if you are interested, essentially what action is doing here is it is writing the following. We can write delegate void, and let's just call it callback type. Here, put some parat and a semicolon. So you can see this looks very much like a method declaration, except it has this delegate keyword in front. Now, what this is doing is it's telling us the type of method that you can have as a listener to an event of this type. So if I replaced action with callback type, the effect is exactly the same because action essentially is doing that same thing over there. The only thing you have to watch out for is that the level of accessibility type, the callback type, has to be the same as the level of accessibility of the event. So we need to make it a public delegate void callback type. And what this is now saying is that anything that has this kind of format, it returns void and it takes no arguments, that can be used as a listener for the on level up action. Now, if you wanted to, you could have a delegate which has got parameters in here. So it could have a float, which I don't know, could be the level, for example, that we've leveled up to. And now you can see over in health, it would be giving us an error because it's saying, hey, reset health doesn't match the delegate. It doesn't take a parameter, so we'd have to take a parameter like float level for it to stop giving us warnings here. But obviously we don't want to do that, and it was fine just as it was. So we're going to go back to removing that parameter, our callback type. You could also have delegates can be used as just parameters into regular functions if you wanted to pass in a callback to be called when a function finishes or anything like that. Delegates are much more widely applicable than the observer pattern, and you don't have to worry about them if you just want to implement the observer pattern. I would recommend using action because it avoids you having to invent a name for something that has already been invented. If you are a C# developer, you will have come across action. So this is something that keeps our code clean. It already has a meaning. We don't need to reinvent the wheel here. If you do want to pass an argument, you still don't need to make a new delegate type because action has a generic format where you put these angle brackets and you could put an action float. And this basically does exactly the same as that delegate I just described. It now means that on level up action expects to take a float. So both the reset health would have to have a float in it, but where we are calling it down here on line 32 in gain experience, that would also have to give you the level, would have to give you a float in there. So we'd have to do something like get level to satisfy the compiler here. So that's a little brief foray into actions. Obviously, I've brushed over them really, really quickly. I'm just going to take away that generic argument for float so that we're going back to having an action that simply signals that something has happened. And this is the most used form of action. So if you see it around the place, event action, this is a common way of implementing the observer pattern in C#. So let's take a look now at the notorious Singleton pattern or anti-pattern, depending on who you ask. So the idea of the Singleton pattern is that you have some sort of object that you only want to list once. You only ever want it to load up once, such as an audio player, or an ambient audio player. You might want this to work across scenes. So you want there to be one, and you want to be able to crossfade audio. There's only one speaker system in your computer, so it makes sense that there's only one audio, kind of central audio player. And that is responsible for crossfading between all the different audio in your game. So if you were to make that decision, then you might decide that if we go and find our Singleton's code here under patterns and we look at the simple audio player CS, you might decide that you want the class to be responsible for making sure that there is only ever one instance here. And here's how it's usually done in a language like C# or even Java or sometimes C++ too. The idea is that you create a static instance of the class itself within the class. So you have something like the ambient audio player class, which has its crossfade new music method, for example. That's basically what we want it to be able to do. But in order to make sure that we only ever get one of these instantiated, we add a private tick member that points to itself. So this is typically the instance started off as null. You then have a public static getter to get hold of the instance. So in another class, you would be able to use it simply by typing something like ambient audio player dot get instance. And you can see that simply goes ahead and would get the instance. Now, what does that do? Well, first of all, it checks whether we've already created an instance before. If we've already created an instance, we just go ahead and return that one. And if we haven't created an instance, it goes ahead and creates the instance. And now, just to make doubly sure that nobody else is going to create a second instance of the ambient audio anywhere in your code, you then make the default constructor private. So that means that no one else outside of this class can go and construct this class. So taken together, this allows us to instantiate a single instance of a class, make sure nobody else does it, and give us a way from anywhere in our code base to access this instance. Now, stop me if you have spotted an issue. Well, it's basically global state. So why is it any better than using global state? I've said static's a global state. We've got this static instance of that variable. We've got a way of accessing it from anywhere. Isn't it just global state? Well, a few things make it better. For a start, a singleton means that we don't pollute any namespaces. This isn't so much a problem with statics. Statics already solve that problem. Statics don't pollute the namespace, but if you had other languages that you're using, like C++, then you can pollute the global namespace there with global variables, and singletons wouldn't. It provides encapsulation, so you don't have to access these static variables directly. You can do it through a public interface that manages the state of that class. Again, statics can do the same thing. You can have private statics and you can have public static accessors, and you would essentially get the same thing without having to create an instance of the class at all. However, the final point is sort of useful, is that it allows us to have lazy initialization. If you didn't want this object to be initialized until we needed it, then it does allow us to do that. But basically, it's not much better than global state, and this is why people see it as being a bit of an anti-pattern. So let's dig in a little bit more into why it's bad. So it's still global state. It can be accessed from anywhere, so it can lead to that spaghetti code situation where you don't know who is dependent on this code. It's not immediately obvious. We break the rule of 3 that you can only do one thing, because suddenly this class is responsible for making sure it's instantiated only once, as well as its usual routine of just doing its job. But in Unity, we often have recourse to want to do something like this because we ultimately can't write any code that has a larger scope than the scene. Everything has to reside in mono behaviors, so we often want those mono behaviors to travel between scenes with us. Now, how could we do this in a mono behavior? Because at the moment we've seen how we can do this just using pure C# classes. If we want to do this with a mono behavior, this is going to be your challenge. So imagine that we had a class that looked very similar to the one that we had previously, except this time it's a mono behavior. And you can go and get the state of the code linked again lecture to play around with this if you like. And the first part of this I've already done for you, which is I've said that on awake, we mark this object as do not destroy on load. You may also need to do something else on awake in order to ensure that this mono behavior is instantiated only once. Take your inspiration from the way we're using statics and that instance variable to see if you can achieve something similar with a mono behavior. And if we get more than one mono behavior in the scene at a time, you can destroy the one that we don't want. Pause the video and have a go. Okay, let's head back into Visual Studio Code. We're going to go to this ambient audio player behavior. And what we're going to do here is we're going to essentially look at whether we are the chosen one when we enter awake. And the way we're going to do that is by having a private static instance. So we're going to have a private variable of type ambient audio player behavior, and it is going to be called the instance. And I've forgotten this needs to be static as well, because we want it to be shared between all instances of the class. And it's going to be set to null by default. Now, when we awake for the first time in the first scene we load, that instance is going to be null. So if the instance is null, we're going to want to set the instance equal to this. And we're going to want to set don't destroy on load as well. However, if this is not the case, so else we have an instance already and we are not that instance, so we need to make this not an else, but an else if the instance is not equal to this, then we need to destroy ourselves, probably the game object that we're on. So we're going to call destroy game object, like so. So now the audio player will make sure that there is only one of it hanging around at a given time. And we can test this out in our scene example. We had this Singleton example with the audio player behavior, and we've got a reloader script which will reload the scene when you hit R. So if we go ahead and hit play now, then you can see we've got our Singleton example here is under the don't destroy and load section. And we can go ahead and hit R and the scene reloads, but we don't get a new Singleton example being created here. It will stick to that initial one, and we probably do get one created very briefly, but it gets destroyed on awake. So that's the Singleton pattern as it's usually used in a nutshell. As I say, try not to use it as much as possible because I do think it violates some of our best coding practices. Sometimes it's unavoidable, but if for those cases, I have got a solution that in my opinion is slightly neater, and we're going to see that in the next lecture. I'll see you there. So let's take another look at how we tend to use the Singleton in Unity. We're only really using it because if we didn't have the pattern, this object would appear again and again and again. Every time we reload the scene or go to a new scene, we would get a new instance, and it would also be set as do not destroy on load. So what we're looking for isn't really the Singleton pattern. It just so happens that this golden hammer has been used to solve the problem. What we're looking for is a way to create an object that is persistent across scenes. And the way I would prefer to do that is to make that the responsibility of a different class, perhaps a persistent object spawner. Now, if you've taken the RPG series, you will have come across this because I have introduced that class over there as well, but I think it's good to talk about it in the context of the Singleton pattern as well. So what we can do is we can go back to our ambient audio player behavior, and I'm going to strip out the stuff here that is to do with only once initialization. In fact, I'm going to remove the don't destroy on load, all of this stuff. Let's just make it an ambient audio player behavior. And all it should do is that. It has a fade music method, which is its only one responsibility. However, let's introduce the persistent object spawner. Now, the persistent object spawner does have some static state, but you'll notice that it's as little state as I can possibly find. It's a persistent object spawner that has a single Boolean. So it's just saying whether we have spawned or not. And how does this work? Instead of trying to spawn a class or anything like that, spawns a prefab. So we configure it to spawn a particular prefab, and it will go ahead and do that unless it has already spawned one. So what happens is in awake, if we've already spawned one because we've done that in the previous scene, nothing happens. Otherwise, we spawn the persistent object and we set that we have spawned to true. And you can see down here in spawn persistent objects, all it's doing is instantiating that and setting it to don't destroy on load so that it will continue to go on through into following scenes. Now, my challenge to you is to go ahead and implement this for our ambient audio player behavior. Because as you can see in Unity at the moment, if I go and load the scene and I hit reload several times, what I'm getting is, well, first of all, my singleton isn't even don't destroy and load. So assuming that it was don't destroy and load, if I had that set up in awake to don't destroy on load the game object, just for the sake of testing it here, we're going to remove that very soon. And we go and play over in Unity. Then we're going to see that when we reload, each time we reload, that new singleton is being created. So I'd like you to try and use that spawner mono behavior, put it in your scene, link it to a prefab, create a prefab that is with the ambient audio player. So create an ambient audio player prefab, add the scene instead, and try reloading the scene now. See what happens and see that you can use this kind of pattern to achieve the same effect as the singleton, but without a singleton and with far less static state around. That static state does need to be there, unfortunately, but it is restricted to this one class, not to the ambient audio player. That could now be unit tested. It could have all sorts of other good advantages that we don't need to deal with. We also don't have that global access to it anymore, so it can't just go anywhere in our scene, and things are a lot better with this setup. Okay, welcome back. Let's give this a stab. So the first thing we're going to do is, as I said, we're going to take this persistent object spawner and we're going to put it in our scene. So we're going to create a new empty, call it the object spawner. And you could use this for everything that you need to instantiate only once, not just your audio player. You can put everything that needs to be instantiated only once into a prefab, which is quite nice. You don't have to worry about doing this singleton pattern again and again and again. So this is telling me that there is not a match here. So I'm going to fix my own typos here. That should have been the persistent object spawner. I think I must have accidentally deleted this at some point. Now I'm going to go over and drag this into our object spawner in the scene. And then we're going to want to create a prefab that is going to be our persistent prefab. So I'm going to create an empty persistent objects. That's going to be turned into a prefab after I've put my singleton example object underneath. I'm going to drag that into anywhere in my assets folder at the moment. I'm going to delete it from my scene because I'm going to be spawning it via this persistent object spawner. So I pop that into an object spawner. I can go ahead and hit play. And now you can see that the persistent object clone is here in don't destroy on load. We've only got one. I can go ahead and hit load. And you can see that no matter how many times I reload that scene, it's not going to spawn those persistent objects again because of the static state, that static variable. So that is my personal solution to how I do persistent objects in Unity and avoid the singleton pattern. I hope you find that useful in your own projects. Feel free to use that code, adapt it, improve it as you see fit. And if you do improve it, share it down in the discussion so other students can have a go too. So let's talk finite state machines. Now, this is a term that if you don't have a computer science background, you probably haven't really encountered, or if you have, it sounds like jargon and mumbo jumbo. Congratulations if you have heard of it. Well, what does it actually mean? Why is it here? Well, the idea of a finite state machine is that you have a finite number of states, funnily enough, and you want to be able to transition between them. So this is great for systems where you have different states that you could be in. For example, locomotion. Here we've got a grounded state, a crouching state, an in-air state, and they're mutually exclusive. You can't be in more than one state. It's also useful for things like AI, where you might have an AI that might have a running for cover state, an attacking state, a looking for ammo state, all those sorts of things. And you, again, mutually exclusive. You can't be in more than one of those at a time, but you can transition them. And the transitions are the key here. In any given state, if you get get some sort of input into the finite state machine, it will behave differently, go into a different state depending on that input. So for example, if you're in the grounded state and you receive either a pressing jump event or a falling event, you're going to move into the in-air state. Similarly, if you are in the in-air state and you receive a land event, you're going to go into the grounded state. But if you press jump or fall while in air, it's not going to transition you anywhere. It's just going to stay in there. And similarly, if you get a land event while you're on the ground, it's not going to transition you anywhere. Now, we could fill out this state machine. For example, if we press crouch, we go into the crouching state. We could transition back by either pressing crouch or pressing jump. So this is kind of a toggle. I press crouch, I crouch. I press crouch, I uncrouch. Or I could press crouch and then I could press jump and I go back to being uncrouched. Now, and finally, if I fall while I'm crouched, I also go into the in-air state. But if I press jump, you can see the behavior is different. I don't go straight from crouching to jumping, at least not in my finite state machine. You could obviously change that depending on how you want to set up your locomotion, essentially. So how do we implement this sort of finite state machine in code? They're very useful. We kind of want to use them in a lot of places. How can we do it? So let's have a look at this locomotion finite state machine monobehavior that I've put together here. Now, the core of it is this enum of state. So here we've got an enum. It can either be grounded, in air, or crouching. And then we have a private variable, the current state, which is initialized, starts off in the grounded state, but we can transition between those states at will. So we can receive any of our public functions. Now, if I go ahead and collapse down these public functions, you can see what they all are. We've got a fall, land, and crouch, which corresponds with the actions we could see on our finite state machine over here. You can check it for yourself. Basically, just 4 actions can be received by the finite state machine, and it's going to react differently depending on what state we're in. So the classic way to do that is with a switch statement. So in here in jump, you can see we are switching based on the current state. So if we are in the grounded state, we are going to move to the in-air state. If we're in the crouching state, we'll move to the grounded state. Now, usually you would do more than this. You may, in a state transition, have to enact some code. So if you're moving from jumping to in air, you play a little jump animation. You may need to change some other stuff there too. You also might need to run some code every frame while you're in the air. So there's other stuff that you can do around the state machine. But this is the kind of core of it. The core is being able to transition those states in the way represented by the state machine itself. And then you can see we can then do the same thing with the finite state machine. You can see if we are in the grounded state, we move to in air. If we're in the crouch state, we also move to in air. But crucially, we are neglecting the other states here, because if you fall while you're already in the air, it doesn't change your state. You stay in the state that you were already in. So you will notice that the land and crouch methods are empty here, and that's because I'd like you to fill out the remaining transitions. So we've already dealt with the press and fall coming out of grounded. We've also dealt with press and fall coming out of crouching. Now it is your turn to try the crouching land transitions. Pause the video and have a go. Okay, welcome back. So let's give this a shot. So the first thing is we're going to put a statement in here. It's going to switch on, again, the current state. Then we're going to need a case of state dot, and let's have a look. So we've got land. Where can we transition land? Only one place, when we're in air. So that's nice and easy. We're just going to say state dot in air. We're going to set the current state from in air to state dot grounded, like so. And then we can simply go ahead and break. And that is land implemented. Now let's have a look at crouch. We're going to, again, switch based on the current state. I'm going to set a case, the first one, crouch from grounded. So state.grounded. We're going to set the current state to state.crouching and break afterwards. And then we're going to put the case where we were already crouching and we press crouch. Then we're going to set the current state to state.grounded. So it just toggles between the two of these. And that is how you implement a finite state machine. Now, hopefully you can see that this isn't the nicest way of implementing a finite state machine, because using all of these switch statements doesn't exactly lead to very legible, human readable code. I'm just kind of trying to rack my head around this. The natural way for me to try and think about a state machine is really state-centric, not transition-centric. This is focused on the transitions. It's saying everything to do with the jump transition is under here. What if I wanted to flip that round and say, what transitions can we have out of the grounded state? Well, that's very unclear in this setup, and that is where the next programming pattern comes in, the state pattern. And that, I think, is a much cleaner way of implementing a finite state machine. And we'll talk about that in the next lecture. So let's take a look at this rather complicated looking diagram. It's not that complicated, trust me. I'm sorry it's a little bit blurry. This is taken from Wikipedia, where somebody has already done the work of putting this together for me, and I think it's useful to evaluate some of the stuff from Wikipedia because the kind of diagrams you're going to come across quite often. So if you Google for state pattern, what is it saying? Well, we have the idea of a context, which is we're coming from a finite state machine. This is basically our finite state machine in here. And then you have the state, except now the state is turned in, instead of being an enum, it is an interface. It is a class. It allows us to say, this is an operation. You can call this operation on me. And what will happen is that in this context, in the finite state machine, something happens and we trigger, for example, the jump operation or the jump transition on the state. And we don't actually know which concrete state we are in. So you could have different states for the different states that inherit from the interface. So state 1, state 2, or jumping, in air, and grounded could be 3 different subclasses, and each of them would implement their own version of jump. And then what happens is, this is the little sequence diagram over here on the right. So the context says, hey, this operation. So it could be saying, hey, jump. Now, state 1 could be grounded. We'll say, okay, well, set the state. Basically goes back and calls on the context again and says, hey, go and set the state to state 2. In this case, it's going to be to the jumping state. And then the next time the operation comes in, jump, for example, well, state 2 is maybe our jumping state, would ignore it and set, or in this case, it's setting it back to state 1. So that's a little bit elaborate from this pattern hierarchy. Don't worry if you didn't get it from that. I just wanted to draw your attention to it. And if you come this after we've had a look at some code, it might be a little bit clearer. So here is an outline of what I've just been explaining. We've got ourselves this locomotion state, which is an interface, as I said. And to implement this interface, you need to implement the jump, fall, land, and crouch transitions. We're going to call the transitions to keep in line with our finite state machine that we saw in the previous video. You'll notice that they pass in this locomotion context. We'll get to this in just a second, but don't worry about it just yet. It's essentially our state machine itself. So then, what does the state machine itself do? Well, instead of keeping track of the enum, as I said, it's going to keep track of a locomotion state. That's referencing this interface here. And whenever we get a crouch, fall, jump, or land, it's just going to call crouch, fall, jump, or land on that current state, whatever that state currently is. Now, one problem here is that I haven't initialized that current state. We do need to initialize it to something. So we could set it equal to a new instance of, and what states do we actually have? Well, you've got a grounded state, in-air state, and crouching state that override our locomotion state interface. Don't override, sorry, that's the wrong word for interfaces. They implement that interface. So we can instantiate an instance of the grounded state. So now, at first brush, if we get a crouch event, we pass it on to the grounded state, and we crouch from within the grounded state. So now let's go and have a look. What happens if I crouch from within the grounded state? Aha, this is where that locomotion context comes in. Essentially what's going on is we are saying set the state on our finite state machine to be the crouching state, so new crouching state. So that's what's going on here, and ultimately I find this so much easier to read. If we're in the grounded state and we go to the crouching state. If we're in the grounding state and we fall, we go to the in air state. If we're in the grounded state and we jump, we go to the in air state. If we land in the grounded state, well, nothing happens. That kind of is honest and makes sure we don't forget about any of the transitions, because if we add a new transition to the locomotion state, to that interface, we have to implement it in each of the states, even if it needs to do nothing, which is a nice mechanism for keeping us honest. Now, I promised I'd circle back to this locomotion context interface. So what have I done here? Here is another interface, and all it does is have this set state function. Why have I done that, and why have I passed that in instead of the locomotion state pattern? Well, two reasons really. The first one is I don't like circular references, so I didn't like the idea that we would have the locomotion state pattern depending upon something like the grounded state or the locomotion state, and then the locomotion state itself depending back on the locomotion state pattern. I don't like it when there are those circular references like that. So it's not a good idea to have circular references. It means things are very, very tightly coupled together. So adding the locomotion context in here inverts those dependencies a little bit. So locomotion state pattern depends on the context and the state. Locomotion context depends only on the state, and the state depends on the context. So those two interfaces are linked to each other, but that's all right when we're talking about interfaces. So then the other reason for this is if I were to expose this locomotion state pattern to the wider world, and I want them to be able to call crouch, fall, jump, land on here in order to manipulate this state pattern, this finite state machine's internal state, what I don't want is another public function here called setState, which would allow them to directly manipulate the state of this mono behavior. So instead, by exposing it through an interface, we are saying you can only use this function if you are using it via this interface. So it just allows us to have a bit of interface segregation. It makes it easier to not make the mistake of setting the state by accident directly, and instead having to use these transition functions instead. Now we do have two more classes down here, the in-air state and the crouching state, which you can see haven't yet been implemented, and you could probably guessed it, that's going to be your challenge. So here is the state machine again for reference. I've crossed out the grounded state and the transitions away from the grounded state because those have already been implemented. So using those as a reference, go in, poke around with the code, get familiar with it, and implement the in-air and crouching states as well. Pause the video and have a go. Okay, welcome back. So hopefully this will be a bit easier because this is a more logical way of thinking about it. So if we're in the in-air state and we crouch, nothing's going to happen. If we fall, nothing's going to transition. If we jump, nothing's going to happen. So the only case where this actually does anything is in the land transition for the in-air state. So in that case, we're going to go to the context and set the state to be a new grounded state instance, like so. Now, if we go into our crouching state and we hit crouch, well, we do want to do something in here. We want to take the context and set the state to a new grounded state instance again, because we are going from crouching to grounded and grounding to crouching and so on like that. Then we've got our fall. What happens if we fall while we're crouching? We're going to set the context set state to in air. So new in air state. If we jump, that is another state where we're just going to transition to grounded. So I'm going to put that transition in there. And if we land, well, it does nothing. We're already crouching. We should be on the ground, so landing shouldn't affect us. So hopefully you can see how the state pattern makes it far easier to write this sort of code. It also allows us to add in code. Perhaps we could have update functions here within an individual state so that there's update functions that are only running when you're crouching, or update functions that are only running when you're in the in-air state. Segregate that code between the states much more easily. In this example, I've put them all under one file. Obviously, in reality, you would probably split each one of these, including the interfaces, into their separate files. But this gives you an idea of how you could use the state pattern for, in this case, locomotion. You could use it for AI, like I was talking about, and you can implement all sorts of behaviors and expand upon this immensely. So if you do end up using the state pattern in your own code, or you have already used the state pattern in your own code, please go and share in the discussions and let us know how you used it. It would be really interesting to see this put to use in the wild by our students. Okay, so let's take a look at a reasonably common situation where we can apply a design pattern that's quite common to Unity and game development in general, which is object pooling. It doesn't only relate to game development. It can be used in browsers, for example, but we'll get to that in just a second. So imagine that we have a very simple launcher mono behavior. And this is how it works. It has a bullet prefab, and in update, if you hold down the space, then it goes ahead and creates a bullet. So let's go into Unity, see this in action. We've got an object spawner object here, and you can see the object spawner has sorry, this is the wrong object spawner. We want to hide that object spawner. In fact, what we want here is the object pool example. And in the object pool example, we've got a launcher. And in here, you can see the launcher script has a link to the bullet prefab. The bullet prefab here, if we go and have a look at it, just has a bullet object, has a sprite renderer, and it has a speed basically on this bullet. Now we can go and have a look at the bullet speed and the bullet script just now. So the bullet script has a very, very simple configurable vector3 speed. In update, it updates its position using the speed and delta time. And when it becomes invisible, it destroys itself. So the launcher is responsible for instantiating it when we hit the spacebar, and it's responsible for destroying itself when it becomes invisible. This is a pretty common paradigm. You may not necessarily do it this way. You might do it based on the extent of the screen. But the effect is that I hit spacebar, the bullets appear on the screen, and they clear themselves up. So you can see here in the sample scene, the bullet clones are getting created and then they're getting destroyed again. Now, this is a little bit wasteful because, as you can see here, we are creating and destroying continuously. That's very better would be to recycle these bullets when they go off screen. Instead of creating a new one, we just use that bullet, we move it back to the spawn point, to the beginning of the gun or whatever else it is. Now, that would be the smarter way. How do we achieve this? Well, using the object pool pattern. So the situation we're currently in is we've got a client, which is our gun. It goes ahead and creates a new object over the course of doing its job when a space bar is hit, for example. And then at some point later down the line, we decide we don't need that object anymore. Maybe it's the client doing this, maybe it's the object itself, doesn't really matter. It goes ahead and destroys the object. Then later create yet another object and do the same process over and over again. And initialization function is costly, not just in Unity, but in many, many situations. You have to create memory, a lot of things, and that is fine when you've got a small number of objects. The more and more projectiles you have, if you have a particularly projectile-heavy game, this might be more of a problem. So the solution is to recycle, reduce, reuse, and recycle. So the way we're going to do that is by having some sort of intermediary object in between called an object. Now what happens is instead of the client creating and destroying objects itself directly, it's going to ask the object pool to get it an object. And if the object pool doesn't have any objects, it'll go ahead and create one. Then it will return that object to the client. Now, if the client has finished with an object, or if the object itself has finished with the object, then it can go ahead and release it back to the object, and that's going to go ahead and call something like disable on the object. It's going to do something to disable that object. And when the client goes to get, again, now the object pool has kept that object around. It's kept it in its deactivated pool, and we'll go ahead and simply enable the object and return the same object. So now instead of and destroying objects repeatedly, we're simply doing a much cheaper operation, disabling and enabling those objects and keeping them around inside of an object pool. Now, fortunately, in Unity, we have a mechanism built in now. Basically, as of Unity 21, we now have object pooling built right into Unity, and it's pretty cool how this works. You can use this object pool object and interface, you see the iObject pool interface, which is implemented by the iObject pool, to create your own object systems. So how does this work? Well, we would create a pool on the client, on whoever's using it. In our case, it's the launcher. You would have to instantiate that pool from something specific. So this is not a great example. I'm going to give you a better example. Let's go into the code that we've got here, download it if you want to follow along. So the client here is the launcher, and it wants to be interacting with an object pool as we saw in our slide. So the way we would do this is to add in a private variable here, which is going to be of type iObject pool, and we have to say what it's a pool of. What's the type that's going to be in this pool? It's going to be a bullet pool, so we'll call this the bullet pool, and we need to instantiate this in awake. So let's create an awake method here, and we do need to include using unityengine.pool in order to get access to this. Then we need to instantiate it to a concrete implementation of the iObject pool interface. So the way we do this is with something like object pool. There are other types of pool here. There's like a linked pool. There's a hash set pool that just have different mechanisms of storing the objects under the hood. I think the easiest for us to deal with at this particular point, and probably the one you're going to use most often, is just the object pool. So let's just go with the object pool. We're going to put in an object pool with the bullet type there again, and then we have a bunch of arguments that we need to pass in here. So let's have a look at what it will complain about. Well, the first thing I'm doing wrong is I need to use the new keyword, and then if I hover over the constructor that we're using, you can see the different functions that this takes. It takes a create function, it takes, and this is not the easiest place to see it, so let's go over to the documentation and see what it takes. We go down to the section in the documentation about the object pool itself, and don't worry, these links will be in the resources for you to have a look at. And you can see that these are the parameters to the object pool constructor. We have a create function. So this is what gets called when we need to create a new instance in the pool if there wasn't already an instance already, as we saw in that diagram. We have an action on get. So this happens every time an object is got from the pool. So that would be enabling would happen like that. Action release. So when we return something back to the pool, how does it get disabled so that it's isn't affecting gameplay or whatever. Basically, this is something that can happen whenever we like. And then we've got the action on destroy. So this is if it gets returned to the pool and there's too many items in the pool, and the pool is configured to have fewer items. As you can see, there are properties further down here for configuring the capacity of the pool. If it gets returned to the pool, the pool's too full and we want to destroy it, then this tells it how it can destroy an object in the pool. So this is all configured through passing in functions to the constructor, which we'll see how to do in just a second. So the first thing we want to pass in is a create function. So we're going to call it create bullet, like so. Again, because we're passing in the function itself and we don't want to be called now, we want it to be called at a later date, then we don't want to put the parentheses on the end. Now I can use control dot to generate a method, and you'll see that it will go ahead and give it the correct signature here, which is that it should return the type bullet. It should return a bullet for us to use. So how do we instantiate a bullet? Well, we've got our bullet prefab here, so you can go ahead and just use this instantiate call from line 21. So I'm just going to cut it out there, and I'm going to paste in the instantiate bullet prefab like so. So I'm going to go ahead and create a bullet prefab, and we want to make sure that we return that bullet prefab like so. And now, how do we go ahead and instead of in update instantiating, we need to be getting an object from the pool so that it has the opportunity to reuse from that pool if it wants to. So the way we would do this is to do bullet pool dot get instead of having what we previously, basically instead of having it instantiate directly. So this now should have the opportunity to reuse if objects are being properly returned to the pool. But at the moment, they are not. They're just simply being destroyed by the bullet. So what happens here is that we need our bullet to have a reference to the pool in order to release itself. So the way we're going to do this is to have a private variable on the bullet, which references the pool. So it's going to be iObject pool, and it's going to be of type bullet. And we'll call this the bullet pool again. And we need to have the using statement using Unity Engine Pool for this to work. We're also going to have a public method here, which I'm just going to call void set pool, and it's going to take in an iObject pool, and we're going to use this as a setter, as you might imagine. I'm going to set the pool from that parameter. Now, that means that in on became visible, instead of destroying the current game object, what we're going to do is we're going to return it to the pool. So we can do bullet pool dot release, and we can pass in ourselves because it takes a bullet. We can pass in ourselves to release ourselves when we become invisible. Now, the final step of the puzzle is to make that link between the bullet and the pool that it's part of. So we can do that in Launcher. In Launcher, we instantiate this bullet prefab. Now, once we've got hold of that, let's just introduce a little local bullet variable by doing a control dot and factoring that out into a variable. Then once we've got a bullet, before we return it, we want to give it a link to the pool. So it's going to be bullet.setPool, and the pool we're passing in is the bullet pool that we instantiated in Awake. So hopefully you're following along. What we've got here is a bullet pool owned by the launcher, created by the launcher. It will automatically create bullets using this create bullet function that we've created here in the launcher. It gives the bullet a link to the pool that it's dealing with. And now, instead of dealing with instantiating and destruction directly, we allow the pool to do that, and we interface with the pool to get and release objects into it. So let's go ahead and see if this alleviates some of the issue we were having previously. So if we go back to Unity and hit play, and then we have a look at what's the behavior. If I go ahead and spawn a bullet, you can see once it's gone off screen, it does not disappear from our scene hierarchy. It isn't being destroyed, it's being returned to the pool. However, it's not being disabled, and also when I hit space, you can see it's not being reset to be at the starting location where it should be fired from. That's something that should happen every time we get a bullet from the pool. Its location should be reset and it should be enabled. So those are two things that I would like to challenge you to do. The way we're going to do this in a couple more parameters here to create to our object pool when we create it. So here, as well as create bullet, we're going to have an onGet, and let's have also an onRelease method. And these two methods we're going to go ahead and implement. So it's going to be control dot to generate the method on launcher, and the same again for onRelease. So now we've got onGet, onRelease. I'm just going to reorder these into the order that makes the most sense. So we get create bullet, onGet, and then release being the final thing in the life cycle. And what I would like you to do as your challenge, no challenge slide here, is implement onGet, so that it re-enables a deactivated bullet, and it also updates its location to be at the starting point of the launcher. And onRelease should disable the bullet so it's no longer visible. Pause the video and have a go. Okay, well, hopefully you've had a little play around in this. So the first thing to do with let's try release actually. How are we going to disable the bullet? Well, I don't want to just disable the bullet. I actually want to disable its entire game object. So I'll do object, which is in this case is the bullet. So let's rename that straight away to bullet, which I think is a better name for this parameter. And then we're going to do bullet.gameObject.setActive false. So that disables the game object on which the bullet is a script. Now, onGet is going to do the opposite of this. So the parameter, again, I'm going to rename to bullet. Then I'm going to do a bullet.gameObject.setActive equal to true. So now all the scripts in that bullet are going to run. But like I said, the other thing we need to do here is set the transform of the bullet, or rather its position. So bullet.transform.position is equal to the launcher's transform.position. This is something we weren't actually doing initially. So this may update the location of our launcher. Let's check where our launcher is. It's down here at the bottom. So I'm going to put it over on the left-hand side of the screen, give our bullet a little bit more travel time across the screen as well. Now I've got an error somewhere in my code. Yes, I've got an extra comma here in this list of methods that I'm passing into our object pool constructor. So let's remove that. And now it should hopefully compile. And once it does, let's go ahead and hit play and start spawning some bullets. So we spawn all these bullets, they start to go off the screen, and you can see as they go off screen, the bullets in the hierarchy are being disabled. So that's the release process happening. The bullets get disabled when they're released. Now, what happens if I spawn some new bullets? Well, actually, no new bullets get spawned, but those bullets that went back into the object pool got re-enabled and reset to the previous location. So you can see that it spawns as many bullets as it needs, but then once those are spawned, it no longer needs them. It goes ahead and disables them. Now, one more thing that you can do with this object pool, there was some other stuff in here, and one of them was the max size. Now, that's just an interesting parameter for us to set. By the way, you can set one of these parameters by name, just like so. So I can do max size to be, let's say, 3, for example. And let's put a comma on the last line. Yeah, that already works. So that's saying set the parameter max size to 3. What's that going to do? Let's go ahead and try this out. So let's restart play and spawn some bullets. So you can see I can spawn as many bullets as I want. That's not what max size is doing. However, let's let the steady state just die down. Well, nothing here has particularly happened. So why is that? That's because we haven't given it a way to destroy bullets. So we need an onDestroy callback to pass into our constructor. We can go ahead and generate that method in Launcher. And this is going to be pretty straightforward. How do we go ahead and destroy a bullet? Well, we do it by destroying its game object. So let's rename the parameter again, as familiar, to bullet. And we're also going to call the destroy method on bullet.gameObject. So that should destroy a bullet. Now, if we head back into Unity and start spawning some of these, then you can see that when it gets destroyed, some of them actually do get destroyed. And you can see that what's left is only 3 bullets because that is the max size of the object pool. So what happens is with an object pool, if you configure a max size, then it will trim back the object pool when objects are released, and some of them will get destroyed if the pool is already size. So you can see we're only ever left with a pool of 3 bullets in this particular configuration, although it will create more bullets if needed at any given point in time. Now, why might you do this? You might do this for resource saving purposes, because if you spawn loads and loads of bullets and you keep them around all the time, then that is increasing the amount of memory your game uses and the amount of resources, even though they are disabled. So that is the object pooling pattern, and now easier than ever to implement in Unity thanks to native support for this object pool interface. So let us imagine for a second that we are writing a special abilities system. And in this special abilities system, you could have one of a number of special abilities equipped, and that could change it while you're playing. You could run into a fireball power-up, and you could get the fireball special ability, for example. Now, very naive and probably not the best way of doing this would be to have an ability runner mono behavior. That's not the problem here, but then configuring the particular ability that you have using an enum. So here, for example, I've got an ability enum, and it could be the fireball, rage, or heal that is equipped at any given time. And we can imagine that this could happen through power-ups or running into different colliders, that sort of thing. But what is clearly visible is that we had a setter for this. You could set the ability at runtime, and then when the use ability public method is called, maybe by hitting a spacebar or clicking a mouse button or something like that, then a switch is triggered here. And depending on which enum we've got selected, a different behavior happens down below. Now, the problem with this is that every time I want to add a new ability, I need to come into this class. If these abilities are more complicated, which they should be, then I'm going to have to add a lot of code into here, and it doesn't add out. So the better way for us to implement abilities is for Ability Runner to have an ability field still, a current ability field, but instead this ability points to an interface, an ability or an iAbility interface, which has a use method. And because it's an interface, it doesn't actually have any code in that use method. It's just defining the contract for what an ability should look like. So then the ability runner would, when use ability, it would call use on the currently set ability. Then we could have a fireball ability, which inherits from the ability interface and actually concretely implement use method. And we could have a rage ability, which derives again from the ability interface and implements its use method. Now, if I were to go and change the names here, what we've just gone ahead and implemented is the strategy pattern. So if we swap out ability for strategy and we swap out use for algorithm, then it is exactly a match for the strategy pattern. And this is what I mean about golden hammer syndrome. If we'd been looking to fit the strategy pattern into here, that would be one thing. But when you've got a problem and you go ahead and solve it with a sensible object-oriented approach, you often find that you have stumbled across a pattern that you didn't realize. So let's try and implement this, and we're going to factor out some of it, and I'm going to leave some of it for you to do in a second. So the first thing to do is I'm going to comment out this switch statement because we no longer need that, but it will be reference for what functionality we want to take elsewhere. Current ability is currently pointing to this enum. Let's switch that up. So instead, and I'm going to do this all within the same file for simplicity's sake, but obviously in reality we would create different files here. I'm going to create a public interface of type I ability, and this is just a C# thing that we prefix interfaces with ability. Depending on the language you're using, that might be different. Now, then we wanted to define a use method, and so let's just, for sake of argument, say it's a void method use that takes no parameters. And it's worth noting that you don't have to put public here. In fact, it's an error to put a public in the interface because by definition, there's nothing private in an interface. Everything is public, so there's no point. So then instead of using the enum, we're going to use our iAbility interface down here. And that's going to be the current ability. Obviously, we can't instantiate this to anything because we need some kind of concrete class. So I'm going to go ahead and create a public class called Rage Ability that's going to inherit from iAbility. In fact, it's not inheriting anything. It is implementing iAbility. And for it to properly implement iAbility, it needs to have a use method. So you can automatically do this with interfaces by doing Control Dot and hitting implement interface. You can see it goes ahead and creates a public void use method that matches the signature in the interface. So now we've got a rage ability. We can use it anywhere where we take an I ability type. So we have this I ability current ability field. I could go ahead and do new rage ability like so, and that's going to give it an initial value. Then over it, I want to actually put some ability into that rage. So I'm going to take this debug statement that we were previously using, cut it out here, and put that into the use method. So now that rage ability can be simply substituted into our current ability, and whenever we call use ability, we're going to do current ability dot use like so. And you may want to wrap this with some checks to see whether the ability is actually set to null, because if it's set to null, obviously there's no implementation for use and it will cause an error, depending on whether you can ever have a situation where there is no ability enabled in your ability runner. So as a challenge to you, I want you to go ahead and implement an iAbility class, subclass for Fireball now and for Heal, pretty much following in the steps that we used for the Rage ability. Pause the video and have a go. Okay, welcome back. So this should be reasonably straightforward, almost a copy and paste job. We're going to have a public class called Heal ability, which it basically implements the I ability interface again. It's going to, we can use control dot to go ahead and implement that interface automagically for us. We can take the debug log for heal and stick it in use, and then we can rinse and repeat for public class. And this time we wanted, what's the other one I have? The fireball ability. And the fireball ability could also implement the I ability. In fact, it must. And there we can put the different code. Now, on this very simplistic example, it doesn't seem like we've necessarily gained very much. But what's useful to know is that one thing we could do with I ability is we could pass in the ability run, or we could pass in the current game object, or anything that could link these abilities back to the world. So in Unity, for example, the game object might be very useful. So in use, we could pass in the game object, which would be the current game object, like so. Now, obviously, this has gone ahead and changed the signature for all the classes, so that's going to cause a compile error. So we can go through and pass that game object in, or just go and change the code so that it has that signature on all of the abilities. And we can pass in the current game object in usability. So we can just pass in game object like so. So this means that these classes are now linked back to the world. So if you wanted to launch particle effects and play sounds and all that sort of stuff, we can do that. We've got a place to spawn stuff. We've got a reference to our world. And now you can see that we could have very complicated functionality going on within each of these classes. And if we need to change anything about the fireball ability, we only do it there. We don't need to go and change this ability runner. In fact, the ability runner stays very, very simple. One more important thing to note here is that because we're only implementing an interface, we actually have the ability to have these abilities be anything we like. So at the moment, they are pure C# classes, but the rage ability could actually be a mono behavior, like so, and we could have the heal ability be a scriptable object. And that opens up a whole world of possibilities. That means the rage ability could be a prefab, the heal ability could be a scriptable object, and as long as you have a way of injecting that into your ability runner, as long as you maybe have an array of serialized fields or whatever goes setting that ability is able to deal with this, then you could do this in a number of ways. And it doesn't matter what they inherit from, it doesn't matter how they do the job, as long as they implement the I ability, that ability to use the ability, then they can be anything you want them to be. And that can be immensely valuable if you want a configurable ability system. You might make your abilities scriptable objects, mono behaviors, or pure C# classes, whatever you want. If you're interested in this sort of stuff, then the RPG series on special abilities, the last episode in that series, is all about creating ability systems, and we go into much more depth, obviously, than I can do here in how to implement that sort of thing. But for now, in the next lecture, to some more depth on this mini ability system into how we can use a different design pattern to make this even more flexible. I'll see you there. Now, suppose that we want to have our rage ability some sort of variant. We want to have a delayed rage ability. Now, the obvious way to implement this is to create a subclass of the rage ability and add in any of the extra functionality that we want there. But suppose delaying something is quite a common piece of functionality, and we want to be able to delay not only the rage ability, but maybe the heal ability, the fireball ability, or any other abilities that we can think of later on. Or alternatively, we want to apply different modifiers, like a repeating modifier to change the way the heal ability heals over time, or something like that. Now, we can easily make this more modular by saying, let's implement a delaying decorator. So the decorator would essentially be another type of ability. It would have its own implementation of use. But instead of entirely creating all of its own rage functionality there or inheriting from rage, it would use composition. It would have an ability that it delays, that is a property, a private property, and that would be an instance of the I ability. So essentially, you could slot anything in there. You could delay any other ability, including, and this is kind of interesting, another delay decorator. So you could delay a delaying decorator and wrap those indefinitely. So what you would get is, instead of having the ability runner pointing directly to an instance of the rage ability, you would introduce a delaying decorator in the mix. So the ability runner would point to an instance of the delaying decorator, which itself would point to the rage ability. And that allows us to decorate or augment the functionality of that ability that is being wrapped. So if we changed out the names, what we've got here is the classic formulation of the decorator pattern. We've got components and operations instead of abilities and use. And the decorator is something that contains one of the components and has its own operation that overrides the operation of whatever the concrete component might be. And you often see this formulation where we take the decorator to be an abstract class that inherits from the component interface, and the concrete decorator often inherits from that. We're not going to do it this way. That's a little bit more complicated. So let's go and see how we can implement a decorator like this. Now, if you feel confident and want to give this a stab for yourself, then do pause the video and see if you can implement this kind of class layout for yourself. Not follow along with me. So what we're going to do is we're going to create underneath the ability interface, I'm going to create a new public class called the Decorator, and it's going to inherit I ability. For sake of simplicity, I'm going to remove mono behavior from the rage ability and the scriptable object, so they are just pure C# classes. Then I'm going to implement the interface, because that will make it a public implementation. So there we go. We've got a using method. It's not implemented yet, because in order to implement it, we need the wrapped ability, a reference to that. So we're going to have a private variable in here that's going to be of type ability, and I'm going to call it the wrapped ability. And that's not going to be set up yet, because we need to set that up when we construct this decorator. But we can now implement the use function that we've inherited here. We're going to do that by calling to the wrappedability.use, and we can do on the line before it to do some delaying functionality. So here we've not actually got an implementation that is really workable in the game, but you get the idea. The idea here is we do some other piece of code before we call to our wrappedability's use functionality. Now, in order to set this up, we need a constructor that will actually take in the ability we're supposed to wrap. You can easily do this in VS Code by doing control dot when you've got your cursor on that private member variable. So we're going to do a control dot and do generate constructor for delayed decorator, and that's going to create as a public constructor that takes in a wrapped ability and sets it to the private property. So your challenge here is going to be to go ahead and construct a delayed decorator instead of that rage ability that we're doing in our ability runner. Make a delayed decorator to wrap that rage ability. Pause to go. Okay, welcome back. So I'm just going to put new rage ability on a new line because what we want to do is set the current ability to a new delayed decorator. And we know that the delayed decorator takes in an I ability itself. So what we can pass in is the new rage ability as the parameter to the delayed decorator constructor. So then essentially what we've ended up with is a current ability pointing to a delayed decorator, which is pointing to the rage ability, which is exactly what we had in the diagram. So hopefully that elucidates how the wrapper, the decorator pattern is working here. Now you could swap this out for mono behaviors, or you could swap it out for scriptable objects. The key that you'd have to work out here is that you would need to point to either a mono behavior subclass here or a scriptable object subclass in iAbility in order for this to work, because you would need to make it a serialized field. So I'll just sketch out what this would roughly look like. This isn't going to be a complete solution, but for example, you would have a public abstract class that would be your base ability SO, and that would inherit from scriptable object and from iAbility, and it would need to abstractly the use method like so, and then in anything that you want to make a scriptable object, you would need to inherit, instead of from iAbility, you'd inherit from the base ability SO, and then instead of having a constructor here, you would set up the link to the wrapped ability as a pointer to a base ability SO and have it as a serialized field, not a serialized reference, like so. And then there's some syntactic changes here. You'd have to have public override because we're using that abstract class, and that just needs a syntactic difference, so you would just do that instead. And that mostly works. You'll need to also pull these out into separate files and have a create asset menu and all that good stuff that you're used to from using scriptable object, but that's the rough outline of how this would work with scriptable objects. So I'm just going to go ahead and undo all of that to leave our code in a compilable state where we were just using pure C# objects. And in the next lecture, we're going to build upon that when we're going to look at the composite pattern, which is related to all of this decorators and strategy pattern family. I'll see you there. Now, suppose we wanted to take the complexity of our special abilities to the next level, and we want to have something like a power attack, which is of sequence type. So this power attack would be composed of other things, such as a particle effect ability, such as a do damage over time parallel ability, and that parallel ability itself would be composed of an instant damage, which might be of a damage ability type, and a delayed damage, which is of the delayed decorator type, and then that delayed decorator itself references the instant object. So you end up with these complicated object hierarchies which reuse a lot of code and allow you or your designers to easily put together new special abilities out of component parts, a little bit like Lego bricks. So if you wanted to be able to do something like this, then you would need the composite pattern, which looks very similar to the strategy pattern and decorator pattern we've already seen. So instead of having a decorator, so if I wanted to have a sequence ability, instead of having one thing that we wrap up in the sequence, which would be the decorator pattern, the composite pattern says, instead of having one thing, let's have an array of things. So the sequence would be an array of children, which are all members of the ability interface. Then my sequence would dictate how how do those children get run? So it makes sense that in a sequence, they would get run one after another. The first one would complete, then the second one, etc., etc. However, if you had a parallel ability for whatever reason and your use was more asynchronous, maybe it started a coroutine, for example, then it would run all the coroutines all at once. Instead, the sequence would probably wait for one coroutine to finish before going on to the next. So you can see how you could come up with different ways of composing arrays of abilities, and that is the composite pattern. Obviously, the formulation is typically more generic than relating to abilities. You'd have these components again, very much the same as the decorator pattern. You would have a leaf, which is kind of referring to the fact that the thing we had before looked a little bit like a tree upside down. So a leaf would be an operation that actually does something. The composite would be the branches of the tree, because it's the branching out points. It says, let's sequence these, let's do these in parallel, etc. By the way, if you've come across behavior trees, this is the way you would implement behavior trees, essentially by using the composite pattern. So how do we go ahead and implement the composite pattern in our ability code base? So let's jump over to it now and give ourselves a little bit more room, because here, before our decorator, I want a new public class, which is going to be the sequence composite, and it's going to inherit from iAbility, and it's going to implement the interface of iAbility, basically the use, and, well, we're going to have some sort of children in here, but you've done this before with the decorator. So I'm not going to hold your hand here. I'm going to challenge you to implement the composite pattern in the same vein as the decorator, remembering that instead of single iAbility, we might want to use an array or a list. So pause the video and have a go. Okay, welcome back. So I'm going to make it a private variable. I'm going to make it, for simplicity, I'm going to use an array that you'd probably want to use a list or something. So it's an array of iAbility, and we're going to call this the children. And we're going to create a constructor which takes in that children array. So when you create a new sequence, you're going to pass in an array of children, and that is going to be set here. Then the use method would do something very, very simple. For example, it would do a for each loop over the child in children, and it would call the child's child.use method, passing in the current game object, like so. So that's a very, very simple way of creating a sequence composite. Obviously, you can have all sorts of composites, as I've just explained. You could have a random composite, one that basically selects a random option from this list. Instead of calling them all in sequence, you could have one that calls them in reverse sequence. The abilities are endless, and you can really split these down into tiny little reusable chunks so that you could easily program all sorts of abilities into this system. So how do we go ahead and construct it? Again, that could be a bit of a challenge for you. I'm going to go ahead and do it. So new sequence composite, like so. Now in here, we need to pass in a new iAbility array, which we're going to construct within here. And in here, you could put something like first we'll start off with a new heal ability as the first child. And then after that, we might run the new rage ability, and then in there, just to show how flexible the system is, we could run our delayed decorator, which itself contains another rage ability. Something along these sorts of lines is entirely possible using our composite pattern. Obviously, you can have composites of composites, and the trees go on endlessly because of this self-referring pattern, because of the fact that the sequence composite is an iAbility and has iAbilities within it, because the delay decorator is an iAbility and has iAbility within it. That's really the genius of these decorator and composite patterns, is that it allows you to wrap them indefinitely into these tree structures that are very, very powerful. So that's it for this little trio of patterns, the strategy, the decorator, and composite. The next video, we're going to be moving on to a completely new paradigm of pattern, the model view controller. I'll see you there. So I have updated the UI here so that we still have our health drain going on here, but now to gain our experience we have to hit this button. We gain experience points until we get to the point where we level up. Still get our particle effect like before, and the health bar still replenishes, but the difference is now we have to do this via the UI, and instead of having our display happen in the console, we've got it happening via our nice UI here. So let's just have a look at what's changed in the code in order for this to happen. So if we go and have a look first of all at the health component, because this is the simplest, what we've done here is we've simply added a serialized field reference to an image component. That image component is over here in the canvas view. You can see there's the bar, that's what it points to. So if I go have a look at the observer example, you can see it points to this bar image. And what it does is on the change, resetting or the updating of the health, it calls to update UI. And update UI simply enters the fill amount of this image. So the fill amount being this little slider here that allows us to fill that image from the left and gives us a health bar. So the same principle is in operation over on the level. We've got ourselves two serialized fields here, the display text for the level, the experience text for the level. And we have also got a reference to a button. So what happens is we again have this update UI called on start and called when we gain experience, which sets the text for these two pieces of UI, getting the level and getting the experience. And we have an increase XP button, which when you click it, essentially just calls gain experience with 10 experience points. So every time you click it, we gain 10 experience points. Now, hopefully, you can see that there's a bit of a problem arising here. All this UI logic added to our level mono behavior is adding complexity. And it's also making it a little bit harder for linking things up. There's more stuff that could go wrong. The observer example, you can see we've got links that go from somewhere, some sort of gameplay object, all the way into the UI. And that link you might forget to put in some places and stuff would break. And then there's more reasons to need to change these classes. So it's basically in violation of the one class deals with thing rule, because here we're dealing with the game rules of the level. We are dealing with handling input and converting that into game rules. We are dealing with formatting of text for the UI and linking to the UI in general, and then Unity is dealing with the rendering, so we're kind of triggering all the rendering and calling into the event system that Unity is using. So how do we typically solve this kind of UI conundrum? Well, MVC is the traditional solution here. So you can see that we break this up into a model, view, and controller. And the fundamental idea is that the model would deal with game rules, the view deal with rendering, and the controller deals with input. So how does this look in principle? The view would initially get its data from the model. It would render that data using probably the Unity UI system in our case, and the user or the player will see that data in the UI form. Then the user interacts with the UI, the controller processes that interaction, and it will update the model on the basis of that interaction. Now, we use the observer pattern between the view and model for the view to observe changes on the model, and so any on-change event will get broadcast to the view without the model having to know that the view even exists. So any on change will trigger the view to update itself and render the new information so that instantaneously the user provides input and sees the results all filtered through the game logic. So how do the responsibilities break down here? The model only handles game logic, often called business logic when you're dealing with business systems. Here it's more game logic related. So things like how many experience does it take to level up? That is the game logic. The view deals with formatting, which we've seen with those text formatting pieces of code in there, or perhaps translating a numerical value to a value on a slider. That is formatting logic. It also traditionally handles rendering. Now, we didn't see that in our code. The rendering is mostly handled by Unity directly, and we just trigger that by manipulating stuff in the hierarchy. Now, the controller deals with processing the input. We saw that with our input binding. It also deals with events and handling those events. Again, that's handled by Unity, but we just listen in on the hierarchy to get our input. So this is traditional MVC, but already you can see that I was saying some things on here are handled by Unity and some things are handled by our own classes. And typically we can't really have this view do anything clever if it is just that Unity side of things. So what we often see is an evolution of the traditional MVC, and we see this also for web development where the view is basically HTML, and so we can't do very much to manipulate the view. You see a different sort of breakdown called the mod enter, and the idea is the same. Let's try and break up that logic a little bit between the model. The model we don't want the model to depend on anything. It just does game logic. So in this situation, what happens? The presenter will go and grab the data it needs from the model, and it will update the view. So the view becomes passive in this model. It doesn't go and listen to the model directly. The presenter is responsible for updating it. Then the view will be seen by the user. The user gives some input, often again to the view. So the view is now handling input as well as what we see, and that seems to match a little bit better with how things work in Unity, because the view in this case could be literally this canvas view. We can see that there's buttons here that would take the input from the user, but also simultaneously we're able to render the stuff in the view as well. So okay, this seems like a better match already. Then what happens? We've got input come into the view. Now via bindings in the presenter we would get events coming through, and then the presenter would update the model. So the nice thing about a model view presenter is that now we've still got, also we register for changes on the model just like we did before, so that the model doesn't need to know anything about the presenters, and you could have multiple presenters hanging off of the same model. So the model still just responsible for game logic. It doesn't need to know anything about your UI. It just needs to expose the data that it knows about. The presenter now becomes responsible for input processing and formatting, the two things that in Unity we are doing in our C# code, and the view layer now becomes responsible for rendering events, which is what Unity is already doing for us in its UI canvas. So this is a much better breakdown that fits with the Unity way of things, and that's what we'll be trying to implement in the next lecture. But before we go on to actually practice, I wanted to talk about another variation of model view controller called the model view model, often abbreviated to MVVM, and you may have heard of this one or come across it in passing. I just wanted to clarify what that is. Here what we get is the model view model is acting very much like the presenter in our MP model. So here the view model will get data from the model, and then via a process of external data binding, properties on the view model will be bound to properties in the view, and automatically when a property changes in the view model, it will get updated in the view. And this is the fundamental difference. Everything else is mostly the same. The view model still updates the model based on an on-change events and so on and so forth, or vice versa is what I actually mean. But the crucial bit about the difference between the presenter and the view model is this little magic binding layer, which if you have to use certain frameworks in order for this to happen. But this essentially means that the view model knows nothing about the view, and the view knows nothing about the view model, which is kind of nice. So to summarize, what we have seen is MVC, where we have the model game logic separated out from the view logic and the input handling in the controller. Then we've seen the evolution of that, where the presenter does handle both the view logic and the input logic, but the view becomes more passive and only deals with rendering and event management. And then we have the MVVM model, which is very similar to the MVP model, with this extra magic of binding between the view and the view model, which allows us to have neither of them depend on each other directly. Great stuff. I will see you in the next video, where we will be putting this into practice to make this UI work a lot nicer. So refactoring our code from this model that deals with everything including UI to a model and a presenter and a view is going to be relatively straightforward, because essentially what we've got here is this level represents both the model and the presenter all wrapped into one. It's dealing with UI logic but also the game logic, whereas the view is already separate essentially because that's what Unity deals with. The view is the bit that does all the rendering and deals with the input events, etc. So what we're going to do is we're going to pull out a level presenter object, and we're going to stick that directly on the UI, and that's going to deal with all of the binding. So this should be fairly straightforward. Let's go in and add a new folder under patterns, which we're going to call the UI, and under there we're going to create a new file which I'm going to call the level presenter. And in here we're going to create a mono behavior, which is going to be the level presenter. And we know from the arrows in our diagrams that the level presenter is going to have references to the model, but also to the view. So we're going to have a serialize field. I'm just going to pop back into Unity to nudge my autocomplete into working. So we'll have a serialize field, which refers to the level object. We'll just call that the level. And we want to take all of the functionality in level that has to do with the UI. So one thing that I'm going to do is I'm going to rip out the using statements for events and UI to kind of give us a hint at where using stuff that we shouldn't be using. Actually, we didn't want to take out events, just the UI layer stuff, and you can see it's giving me squigglies under the text and button types, because those UI types, we shouldn't have anything to do with those UI types in a model. So we're going to pull those out, there's 3 of them, and we're going to stick them into the level presenter. So this now makes sense. The arrows of our dependency from our presenter match up with the arrows from the diagram in the last lecture. We've got a dependency on our model and 3 dependencies here into our view, which is essentially the canvas hierarchy. So what we're going to do here is we need to take a little bit more action in order to take UI, update UI out, and to take the increase button binding in here out as well. So first of all, the button binding. This is relatively straightforward. I just need to create a start method in a level presenter, and then we want to put our cut and paste increase XP button binding into here. And we want to, instead of calling gain experience just on ourselves, we could introduce our own gain experience method in here. We're going to just go ahead and generate that method locally as a private variable. And within there, we can just call level.gainExperience10, because that's a publicly accessible function, and that's fine. The model does present us with an interface of how we can gain experience. So that's fine. Now, the other thing we want to do is essentially have some sort of private void method called update UI in here. And we want to take the implementation essentially of update UI out of, or cut it out from the level model and put it into the level presenter, like so. So that works, except now we need to be, instead of calling get level, we need to be calling level.getLevel and level.experience, get experience. And now the final piece of the puzzle. When do we actually call update UI? Well, one naive implementation would have it called in update, but obviously we don't update the experience every frame, so that's a little bit wasteful. So the way we want to do this is, instead, in the places where we were previously calling update UI, we want to break that link so that model is not dependent upon the level presenter. So the way we're going to do this is with an observer pattern, which we've already done this with the action for on level up action. So I'm going to create event type action, which is going to be on experience change. And on experience change is essentially what we want to call here. So in start, we're going to do an if on experience change is not null, We want to call on experience change, and we want to do the same thing down here where we were previously calling update UI. If we gain experience, we're going to do on experience change there as well. So in actual fact, I don't think we need to call it in start, because in start, the UI presenter knows that it should get some initial values. So what we're going to do here in level presenter is we're going to register on that observer. So we're going to look for our level dot on experience changed. We're going to add a listener, which is going to update the UI when the experience changes. And just to give an initial value to those UI elements, we're going to also call update UI in start. So we'll listen for changes, but we'll also initialize ourselves the first time. So this is a nice, neat model. It means that our level no longer even needs a start method. As you can see here, it's now entirely dealing with its own game logic, and it's just calling to observers when certain relevant events change. So things can hook into when the experience changes, when the level up action takes place. That's nice and straightforward. We now need to set this up over in Unity. So we'll go back into the editor, and on the canvas object, I think might be the natural level up from these UI elements. I'm going to add a component, which is going to be our level presenter. The level presenter needs hooking up to some different things. So the first thing it needs hooking up to is the level text. It needs hooking up to the experience text and the increase experience button. So we hook all of that up. And then we need to hook up the actual level model script, which is on observer example. So we can just pop that in there. And now you can see that on the actual observer, we no longer have all these dirty, horrible references to UI. That's all gone. It's now the UI itself, or rather the presenter, that is hooked up into the model. So if we go ahead and just check that everything is still functional and working as we would like it to, you can see that by gaining experience, I can eventually level up. So my button input is working, my UI presentation layer is working. All that remains to be done is to do the same thing for the health bar. So here are the steps for you to take to make your health MVP. You're going to create a health presenter class, MVP class. You're going to move the logic over from the health model. Anything that's to do with UI, you're going to move into that presenter class. You're going to add observers to the model so that the presenter can hook into those observers without the model knowing anything about the presenter. And you're going to hook up all of the dependencies in Unity. Pause the video and have a go. Okay, welcome back. So we're going to go in and create the class first of all. So a new UI file called health presenter.cs, and we're going to create a mono behavior within here. Then we're going to go over to our health model. We're going to eradicate the using Unity Engine UI and move it over to our presenter so that we can see what needs changing. What needs changing is this health bar image reference that needs to come over to the health presenter. And like I said before, we also need a serialized field, which I'm going to need the autocomplete for. So I'm going to go back into Unity Engine, have it just bump my autocomplete so that I can now do autocomplete for serialized field. And I'm going to have a serialized field to the health component, which I'm just going to call health. So that's the health model essentially. And then we need to have a look at where we've got our update UI. I'm just going to take the update UI method wholesale over into our health presenter, like so. We are then going to need to call that in our start method. So we're going to add start and we're going to call up in here. We're going to need to, where we've got current health and full health. This is not currently exposed, I think. We've got get health, but we don't have a get full health from our model. So we could have that exposed. We'll have a float get full health, which is simply going to return the health variable out of there. So now we need to update this code so that it does health.getHealth and divide that by health.getFullHealth, like so, and that's going to achieve the same thing. Now, if we go over into our health thing that we need to do is have some sort of notification method, because we can see that we're updating the health when we health drain, we're updating the health when we reset the health, and that needs to notify any potential observers. So we're going to add a public event of type action called on health change, and we are going to call this where we were previously calling update UI. So we're going to say if on health change is not equal to null, then we're going to do on health change parentheses, and we're going to do that same thing over in health drain, so when we change the health value by decreasing it over time. And that should call to anything observing. Currently the health presenter is not observing, so in start we do want to set that up. We want to do a health dot, and on health change we're going to do a plus equal and add update UI to be called as an observer. So now what will happen is the first time on start we'll get an initial value from the health, and then thereafter we are going to update ourselves when the health system tells us to. So if we go and check doing the first reset in awake, which is great because start is going to happen after that, and get the fully set value for health. So let's go over into our editor, let things recompile, and we just need to hook everything up now. So on the canvas, I'm going to add our health presenter mono behavior, and now we need to hook it up. So first of all, where is the health image? Well, it's the one called bar here. So I'm going to drag that in. And then I need to drag in, again, the observer example, which has the health component model on it. So if we go ahead and hit play now, hopefully everything should be unchanged, and we're still getting the decreasing happening on a regular basis because we're getting those events come through. If I add enough experience and it causes us to reset the health, that also comes through and instantaneously updates the UI. So essentially what we've got from a functionality standpoint is completely unchanged, but now we've split that into two separate classes. One that deals with gameplay, albeit health and level, and two that represent UI, which is the level presenter and the health presenter. And we notionally have a third level of abstraction here, which is the view itself, and that's all handled passively, essentially, in Unity. There's no code that we're writing that handles it's all pushed and manipulated by this middleman, which is the presenter. So hopefully that's made it clearer for you what Model View Controller is, what MVP Model View, and how it's relevant to games and your implementations in Unity. I'll see you in the next lecture. So that brings us to the end of the programming patterns that I wanted to cover in this mini course. However, there is plenty more to learn, lots more stuff out there, and I wanted to leave you with a few more resources to get you going. If you are interested in any patterns I haven't covered here, hopefully the fundamentals covered here will give you the basis to understand some of those patterns in more detail. So a great resource that I use all the time is Refactoring Guru. I've left a link in the resources. There you not only cover lots of design patterns, but lots of types of refactoring and when to apply that refactoring to your code. Next up is Game Programming Patterns. This is a book, again, link in the resources, and it's a fantastic book that applies a lot of programming patterns to games, not specifically to Unity, but there are a bunch of things there, such as the entity component system that I haven't covered in this course, that is covered in the Game Programming Patterns book, and is a very interesting read. Then we've got Clean Code, which is by Robert C. Martin, who's an absolute god of programming. And if you are interested at all in the stuff in this course, then a lot of that was influenced by this book and also Robert C. Martin's work in general. He's kind of the godfather of the solid principle, so that also comes from him. And finally, a little bit of a cheeky one, the RPG series, the course by yours truly, goes into a lot of detail in not just programming patterns, but general good practice in writing code for large systems. The RPG is a huge course, that's why it's 4 courses, and it's a huge project, so we have to deal a lot with change management and how we deal with changing requirements and how we make code maintainable and modularized and acyclical dependencies and all those kinds of things. So if you're interested in this and want to see it on a larger scale, then the RPG series is an excellent epic for you to follow. Now, I'd be interested to hear from you. Please go and share in the discussions what your favourite patterns are, maybe ones that weren't covered here. Is there anything that you really loved wasn't covered? Can you explain them in the discussions? Can you give your best possible explanations? Have you ever used them in a game? If so, for what sort of mechanisms were they useful? Do let me know down in the discussions, and thank you ever so much for being part of this course. So lots of the early testers of this course asked me whether I was going to cover the solid principles, and at first I wasn't thinking of doing it, but because I got so much request for it and to know how it fits in with my coding commandments, I decided that it would probably be worthy of some bonus material. So here are the solid principles, originally originated by Robert C. Martin of clean coding fame and other books, and just generally being a behemoth of this space. So a little word of caution, and this is something that Robert C. Martin says himself in his original paper on the solid principles, is that following the rules on the paint won't teach you how to paint. And this is important. You can't just follow the rules and expect to be an amazing programmer. There is lots of skill involved. It's a craftsmanship, and you need to do it with experience. And if you don't know when to break the rules as well, that is a problem. So these rules are to be followed with caution and to be done with skill and applied judiciously. So let's have a look at the single responsibility principle, the S of the solid principles. This is very straightforwardly already in our commandments. I think it was 0.3 or something, that a class should have only one reason to change, should have ultimately only one responsibility. I don't think we have to dig into this one too much. It's a very good tenet of object-oriented programming in general, and it's important to note that all of these principles aim to deal with change management. If you have changing requirements in the world and you're writing software for a changing requirements world, then you want your software to be flexible and allow you to easily adapt to new requirements. So all of these are trying to aid you in that purpose. So having a class responsible for just one thing aids you in that purpose by allowing you to know where to go to make that change, and also to have changes destabilize as few things as possible. The open-close principle. Now, this is probably the crux of the solid principles, at least as Robert C. Martin puts it forth, and it's also the hardest to understand. So, at its core, open for extension but closed to modification. What does this mean? Well, it ultimately means that you can create subclasses, or you can create extensions of an interface, but without modifying the stuff that people are depending upon. So we're closing down the interface so that we can easily depend upon it, but then we're allowing extension of it to add new functionality. So attempting, again, to make things easy to change by adding functionality through extension, but hard to break by keeping it closed for modification. Now, how do we typically do this in something like C# or Unity? Well, we typically would use interfaces because we would rarely modify the interface. That's closed for modification, but we would implement extensions or implementations of the interface which allow us to implement change. And the same thing with abstract classes. You might make the abstract classes interface closed for modification, but open for extension. So let's take a look as our example from the programming pattern we've been using. The strategy pattern is a classic example of you implementing the open-close principle. In the previous example where we had just the ability runner and it worked on the basis of a switch statement or an enum, then obviously this was a problem, because if we wanted to make any changes, we had to go and change the ability runner. So this was both open for extension and open for modification. Not what we wanted. So using the strategy pattern, we pull out an interface for the ability. Now that interface is closed for modification. We very rarely going to change the number of methods on that interface and the parameters to that interface methods. That's closed for modification, but open to extension, because we can add in new abilities really easily, and it allows us to adapt to new gameplay requirements. Our game design decides, hey, we need this new ability. You can easily go and add it by extension. So the next thing, we've had S and O of our solid principles. We now have the L, which is the Liskov substitution principle, named after Barbara Liskov, who states it like so, that subclasses, or this is how it is stated sometimes. I think it's been stated by Barbara Liskov in a bit more of a mathematical sense, but here is the crux of it, that subclasses should be substitutable for their base classes. And you're probably looking at this and going, why is this even a thing? This is obvious. Obviously, if I have a subclass, I should be able to substitute it for the base class. That's entire. Well, yes. I mean, obviously, the interfaces will be substitutable, but the point is they also need to be behaviorally substitutional. So an example here is with rectangles and squares. So we've got a client that might have access to a rectangle class, and that rectangle class has a width and height. Now you might easily say, well, a square is just a rectangle. It's a rectangle where the width and height are equal. Cool, that sounds like a reasonable thing. Now on our rectangle, we've obviously got set width and set height and get width and get height, and that seems reasonable. So when we're using the rectangle, we might happily say, let's set the height and set the width, and then we can assert that the height that we set is actually the height that we get back when we do a get height. Seems reasonable enough. The problem is we inherit a square, which also seemed like a reasonable thing to do. It has the same but to do this, because we've got this extra height and width property that in a square they're the same, we override their setters so that the width and height always get set to the same. And suddenly we have a problem, because if we substitute a square into that client code that we've got over here on the slide, this assert isn't going to be true. When we go and set the width to 3, it sets both the width and height to 3, and so overrides the value that the client was expecting. And so here, apart from the programmatic interface that we have to this rectangle class, you've also got some sort of implicit interface about how it should work. You've got the implicit that if I set something, I expect it to still be there when I get it back. And so this fails in terms of substitution, Liskov substitution, and all sorts of bugs can arise from this. This is a very simplistic case. However, there are many such cases that are harder to find, and one typical example in object-oriented programming is equality, where equality gets redefined further down the inheritance hierarchy and can break when you substitute a child class in for a parent class. Now, I'm not going to go into details of how that breaks down. I'll leave a link in the resources to a discussion of equality and Liskov substitution principle, but it's interesting further reading if you want to go down that rabbit hole. Now, interface segregation, this is the I of solid. What does this mean? That many client-specific interfaces are better than one general-purpose interface. So, for example, imagine we have a health component that we've been working on in this course, and it was being used in potentially multiple places in the UI to display the health, but also combat to subtract from the health. Now, what we're saying is that those are two very different cases by two very different clients, so perhaps we'd be better off having an interface for each, maybe an I health display to facilitate the interface for the UI, and an iDamageable for combat code. And the reason this is a good thing is that it allows us for all sorts of damageables later down the line. It allows us to swap the health display to something else. It also means that there are fewer opportunities to accidentally get extra dependencies in there. So, for example, the UI accessing that it shouldn't, and later causing problems when we need to refactor our health component. So it keeps those dependencies kind of segregated in this interface principle. And finally, the D of the solid principle is dependency inversion. What does this mean? This is typically implemented with interfaces. So depend upon abstractions, do not depend upon concretions. Now, the idea here is that suppose you have your game code and you are depending on a concretion. You're depending on a concrete system, such as the Unity Audio subsystem, or maybe your asset pack, Super Dialogue System X, that you've downloaded from the Udemy Asset Store. Now, everything is well and good until you realize that, oh no, you know what I wanted to use actually was Super Dialogue System Y, because it has this really cool feature that I need. And hey, Unity Audio System just isn't quite cracking it for me. I now need the Fmod subsystem to do the work much better. Now, you've obviously got a headache because you've hard-coded all of the interfaces of the Unity Audio System and the Super Dialogue System into your game code, and you've got to go and change a whole heck of a lot of code in order to swap these two out. So the dependency inversion principle would say, instead of depending on those concrete subsystems, why don't you depend on an interface instead? So you depend on a dialogue system interface in your game code and an audio system interface, and that would define how you're going to interact with these subsystems. And then the subsystems would all inherit from their relevant interface. And now swapping them out becomes a doddle because their interfaces are the same. Now, obviously, you can't make the Unity Audio subsystem conform to your own subsystem interface. So for this kind of thing, we might use the adapter pattern, which is a little bit like the decorator pattern in its structure. But the idea is that we would put a little component, a little object in between that implements the audio subsystem interface and uses the audio, basically a translation unit, and translates from your audio subsystem interface into the Unity audio subsystem interface. That is a situation when you can't change the actual code itself. You can add those little adapters in. Again, if you're interested in the details of the adapter pattern, do go and have a look at the resources, because I've linked to Refactor Guru there where they do a very good explanation of that pattern. So those are the solid principles. The single responsibility, where we say a class should do one thing. Open closed, meaning that we should allow extension of interfaces but not modify those interfaces too much. The Liskov substitution principle, where we're saying that behaviorally, if there is some sort of implicit contract on a parent class, we should obey that in the child classes. The interface segregation principle, which means splitting out interfaces for different clients, so there's less reasons to change those. And the dependency inversion principle, which allows us to swap out large bits of concrete implementation to keep our game code, or any code really, less fragile to change. So hopefully you found that interesting and you've taken away some points that you may want to use in your own projects. If so, please do go and share them in the discussions. I would love to hear your thoughts.